This is the definitive beginner's course on robotic imitation learning using AI. This course is for people who want to learn how to teach robot arms how to complete tasks independently on their own, like picking up this blue ball and placing it inside of this box. Or even more complex tasks, like being able to fold a t-shirt. Now, I didn't program the arm to do any of that, I just showed it how to do it. And by the end of this course, you'll have built this yourself from parts, trained it, and understand exactly how it works. Oh, and I'm Brogan Pratt. I've been teaching robotics and design for over a decade now, and I've mentored thousands of students to do just the thing that you're about to do. And this project doesn't require any code, so you don't need to have a technical background to be able to understand these complex concepts either. And I'll build it up logically, step by step, so you won't be left behind. So let's get into it. Now, this is going to take part in 7 different parts. The first part is talking about what sort of parts are you going to need to be able to actually assemble your arms. We are going to be using the So101 arm from a lab called LeRobot. They are one of the forefront AI training models with low-cost tools for robotic arms, and they have done a good chunk of this work to be able to do this that we'll be using throughout this setup. Then I'll step you through how do we actually assemble the arm together, how do we put the motors where they need to be, how do we put the wires where they need to be, and it gives some tips and tricks throughout the way. Then we'll set up our computer to make sure the things are ready to go. What type of computer do you need? Because this will even work on low-spec machines as well. How do we actually set up the arms to be able to communicate with the computer, because we're going to plug them in being USB ports. Then we'll actually train that arm to be able to complete the task. So how do we take that black leader arm, move it around, and then show the follower arm how to complete a task that we want to do? And there's a large variety of tasks that you can teach these arms to be able to do. Then we'll actually train an AI model based on our training data. And that sounds super complex, but don't worry, you'll be able to do it in just a couple steps. And then we'll actually run that trained AI model so that we can have the arm actually do our bidding. So that's kind of a big overview. Let's get a little bit nitty-gritty into what we're going to do in each of those parts. When we talk about part 1 and all the parts you're going to need, we are building something called the So101 arm from LeRobot. Is designed to be in a leader and a follower method, which means you have one arm that shows the other arm what it is it's going to do. I'll show you all the parts you're going to need, whether you want to 3D print it yourself and buy all the parts, or I'll show you some options where you can actually buy pre-built kits so you don't need to build it yourself. Then I'll talk about what kind of computer specs you're going to need, and you don't need a very powerful computer. The computer I'm doing this on is almost 10 years old at this point. So you can do it even on low-spec machines as well. In part 2, when we talk about assembling the arms, I'll go over what every single part does and how it works with the arm, and I'll step-by-step walk you through how do you actually build these arms together so that you don't get lost. We'll talk about pre-wiring the arms up, as well as mounting some of the motor controllers so we can actually tell the motors what to do to be able to move the arm around. And then I'll give you some tips and your tricks to be able to set up your ideal imitation learning testing setup. And that basically means what should your workbench look like for you to be able to have a successful time doing imitation learning. In computer setup, whether you're using a Windows, Mac, or Linux PC, I'll show you how you can actually get all the different software that you're going to need to be able to run these arms to be able to teach your own robot training. Then in part 4, we'll get to the arm setup. And this is where how do we actually make the arms communicate with our computer? How do we set up our USB ports? Because it's not as simple as simply plugging in a cord. We need to tell our computer where to go. How do we set up individual motors? How do we finish wiring those arms? And then how do we calibrate the motors start and stop points so they know how far they're allowed to move? And at this point, we'll actually get into first teleoperating your arm, which means when you physically move your arm around, the follower will follow what the leader is doing. And then we'll get some cameras set up because we need a few cameras to be able to do this actual training. Then we will train an arm to be able to complete a task. And at this point, we'll talk about what the ACT model is, the AI model we're going to be using to be able to do our training, and how does it actually work. We'll talk about doing a recording data and how do you actually record an episode, which is a full completion of the task. So how do you go pick up the Lego piece? How do you go move the pencil? How do you write the word? How do you fold the shirt? We'll do some test recordings and I'll step you through how that works. I'll step you through if you make a mistake, how do you actually resume a recording, and then how can we play back recordings so we can see that the data is going to be useful for our AI model. And then I'll show you how to actually record a full set of training data so that we can feed this training data into an AI model later to actually train. Once we have trained our arm to complete a task and we have completed some of the data, we'll actually train the AI model. And you'll understand how the AI model works on the back end so that you'll be able to actually train it and have it run its own model. I'll show you how to both train that model locally and train that policy online. And it sounds like a really big idea, but trust me, it's about 2 lines of code and then we'll be able to actually have that training model running for us because we're using the LeRobot guys who have actually made the model and we're just feeding some data into it. And then we'll talk about how do you actually use that training data, how does that training work so you can understand some of that more back-end understanding from what the LeRobot team has actually come up with. Then once we've finished training our model, we'll actually run our AI model. And at this point, you will have an arm that is able to complete the task independently by itself, recover from mistakes, and be able to follow along with the task that you've given it. And that is effectively putting it all together. And then throughout the entire video, I'll be sharing some debugging notes, some tips, and some different tricks for you so that you can find some success and avoid some of the common pitfalls that happens when you're trying to set up some robotic AI imitation learning from the start. So let's talk first about what parts you're going to need to be able to build your own leader and follower arm with the SO101. Well, let's start first about the robot arm structure itself. You got 2 options. First option is you can 3D print these parts all yourself. Now the GitHub project has all the files you're going to need, so you can just print out those down below. If you go to github.com/therobotstudio/SO1 SO-ARM100 and come down to the printing the parts heading, you can find all of the files that you need. Of course, it tells you how to choose a printer, setting up your printer, so on. If you already know how to do some 3D printing stuff, that's great. You can move on. Otherwise, there are some tutorials here on how you can set things up. You can check your printer for accuracy. I recommend that you do this. Now, if you're using a bamboo style printer, I'd suggest you use the gauge 0. Those work for the bamboo printers I found. It also works on Prusa. I found that it was not necessary to do a gauge tight for my prints. Now for printing your parts, doing that specifically, they do have 2 full print beds set up. I prefer to print the individual parts files where you can find the individual STL links as well. And then we'll also talk later in the video about how many of each part that you need. In terms of types of plastic to use, because you don't have a lot of lifting weight for this, PLA works perfectly. I've personally been a fan of PCTG lately for robotic stuff just because I find it's a bit more impact resistant, lasts a little longer. But again, any sort of bog standard PLA is going to be just fine for that. Another option is that there are services that either sell these as full made kits, so you don't actually have to purchase all the individual motors, all the individual or 3D print all the individual parts, get all the power supplies, things like that. If you just want to get up and running, you can use one of those kits. If you'd rather not go through the hassle of sourcing all the individual parts you need, in my opinion, it's not that crazy. But if you don't own a 3D printer, there are options for you. There are kits that already exist. You can do things from things like internationally or United States, China, South Korea, EU. Some of these kits also include fully assembled versions as well, if you'd like that. Other of these are just the parts that you need. Other of them are just the 3D printed parts, not including the motors and power supplies and things like that. So make sure you check from your specific supplier if you are going to go the kit route. If you're going to do more of a DIY route, let's talk about what it is that you're going to need to be able to build one of these. Now, first things first, let's talk about the 3D printed parts you're going to need. You need a base motor holder. That is this guy, and you're going to need 2 of these, one for the follower and one for the leader. You're also going to need the motor mount itself, and this sticks on top of our base motor here that holds that motor in. Again, you're going to need 2 of these. Next up, you're going to need the pivot arm, which is this guy, and this is the part that actually pivots the shoulder. You're going to need 2 of these as well. On top of that, you're going to need the shoulder joint, or the actual shoulder itself, which is this guy, and a motor holder for that shoulder, and you'll need 2 of these as well. Then you need the elbow, which is this guy. You'll need 2 of those as well, 2 more of these motor holders for that elbow. And then you need 2 more of these. This is the actual wrist on the robot. Now comes some more specific parts. For the follower, you're going to need the bottom of the arm here. You can also print these off in a compliant wheel, and you also need the other fixed portion of the claw. Now, I really like this design here because it has the ability to put in a camera on the claw, which is going to make your training a lot more accurate, as opposed to getting a design that does not have a part on the claw. Now, these 2 are specific to the follower. And then on the leader, you have slightly different handles. So you have a pistol grip as opposed to a fixed claw here. And then you have a little trigger here as opposed to the other section of the claw itself. But otherwise, those prints are the same. And that's what you're going to have to print out. Now, there are full build plates for certain size of build plates set up on the GitHub repo, so you can just print off an entire section. I prefer not doing that because sometimes I find if you can start a 10 or 15 hour print, if it has the chance to fail, I prefer just to print a couple print parts at a time, in my opinion. Let's talk about the computer that you're going to need. Now, this tutorial is designed in such a way that you do not need a very powerful computer. I'm currently running this on an M1 Mac from about 5 years ago. I've also run this on a Windows PC with a Ryzen processor on it that's from about 6 or 7 years old and a pretty old AMD graphics cards. You don't need a very powerful computer. Now, you can train this on a Mac, you can train this on a Windows, you can train this on a Linux. Bear in mind, if you are going to be using a Windows, there are some funniness things that are going to pop up, and I'll make sure I leave some notes for those Windows users in my notebook down below and throughout the video for you as well. In terms of all your parts you'll need, if you go to the sourcing's parts section, you can scroll all down here for parts for 2 arms. This is what this tutorial is going to be following. We have the follower and the leader set up, and there are notes on how many of each thing you need to order. There's also notes on whether you're buying things specific from the US or buying them from the EU or buying them inside of China or Japan, depending on where you are located in the world. All those links are right there. And then I believe if you purchase these through Amazon, I'm not sure about Taobao, but it does end up giving the LeRobot creators a bit of a kickback as well by using their parts through their Amazon links. So also a pretty sweet thing to keep in mind. Make sure you check the parts numbers as you order these things. Now, keep in mind, you can also swap to the 12 volt inside here where you should use the separate 12 volt power motors there, but we'll talk more about that later. So now the servo motors themselves come with a 3-pin wire, which you're going to need to obviously connect the servo motor. They also come with all of the screws that you're going to need to be able to mount these things in. They come with an M2 and an M2.5, so you don't have to actually buy any screws, which is nice. And then they also come with the servo horns themselves to be able to actually mount our arm components onto it. So you don't have to buy anything additional with these servos. They come with all the mounting hardware as well as the wiring hardware that you're going to need. Now, when it comes to the amount of servos you need, if you're going to build 2 follower arms, or every single follower arm needs 6 of these VTech STS 3215 motors. And we're going to run the 7.4 volt version here. And the followers all need 1 to 345 gearing, which is going to give you lots and lots of torque. Well, I say lots and lots of torque, but it's going to give you a good amount of torque. There is the option on your follower to, instead of using a 7.4 volt, which has a stall torque of about 16.5 kilograms at 6 volts, you can also use a 12 volt version, which has a stall torque of 30 kilograms. In my opinion, the 30 kilograms is a little bit overkill because for this small arm, you have a capacity load of about 500 grams, which is more than enough for some small AI-based training. But if you want to lift up some slightly higher, maybe, 750, 800 gram working load, you can use the 12 volt system. And we'll talk more about that with the actual power supply that you need. Now, for the follower, you do need the 1 to 345. But for the leader, it's a little bit different. For the leader, you need a single 1 to 345. And that of the same motor, you need 2 of a 1 to 191 gear ratio, and you need 3 of a 1 to 147 ratio for the follower. So you need 1 345, 2 191s, and then 3 147s for the leader. But for the follower, they're all the same. It's just all 6. You're also going to need some way of clamping the base to your table so this thing doesn't fall off. You can get a couple clamps. These are just simple woodworking clamps. Doesn't have to be anything crazy. I really like the Irwin quick toggle clamps or quick grip as opposed to these, but these work. They're cheap. You're going to need 2 USB-C to USB-A cables. Could also be USB-C to C, that's okay. But the motor control we use does require USB-C. So you need 2 of these. Make sure that they're long enough that they can actually reach your computer. If you're going to be using a MacBook Pro or a laptop for this, you may also consider getting yourself a USB 3.0 hub. Then you're going to need 2 motor controllers, 1 for each robot. And I'm using the Bus Servo Adapter A from Waveshare version 1.1. Again, I'll have a link to those in the description down below. Now, Grove Studio also makes a motor controller here. I prefer the Waveshare one, but again, it doesn't really matter which one you use. What will matter is the plate at the back that you're going to be printing off. This allows you to, at the back of the robot arm, basically slide in your motor controller so that it sits on top like so. It'll just depend on whether you're using the Grove or the Waveshare, so check which parts you're going to need. Then you're going to need 2 power supplies. I'm using these ones from Leica. It's got a EU power supply, but again, you've got ones that will work for North America as well. This is a 5-volt 4-amp output at 20 watts. So if you have some kicking around that have a standard barrel jack connector, then you can go ahead and use those as well. If you are going to be using the 12-volt servo motors as opposed to the 7.4-volt servo motors, you should make sure you get yourself a 12-volt system as well, something that has at least 5+ amps on your system or on your power supply. The leader will always use a 5-volt 4-amp 20-watt system though. Now, the last thing you're going to need here is a couple webcams. Now, I'm using a 1920 by 1080p webcam here. The biggest thing on your webcam is you want it to have a nice wide field of view so that you can actually record and look at your robot arm as you're doing your training. I'd also recommend that you pick yourself up a 30 by 30 little USB camera as well, because this allows us to get views from the claw, and that makes life a lot simpler. This one is a 34 by 30 camera. It's just one that I had kicking around, but it will still work just as well. If you have a MacBook, you can also use the continuity camera on an iPhone if you'd like. But I'd highly suggest that you do not use the just base webcam from your computer, because you're likely going to be, or if the computer is a laptop, I would not suggest using that webcam, because you have to have full view of your follower arm while you're doing the whole training, and that's going to make your life a bit of a pain. If you do decide to go the external webcam route, there is an optional print here you can use. It's just kind of a little print tower, and this makes it a lot easier to mount your webcam on top so that you always have a fixed position for your webcam to always be looking at. And again, I'll have links to these in the description down below. Last thing you're going to need is some sort of precision screwdriver set. You need a Phillips number 2 and a Phillips number 1 for this tool. If you don't remember the Phillips are those little cross or the little plus heads or the stars, depending on where you're at. I really like this kit from iFixit, but you do need some sort of precision tip here because you need a small tip here. A standard large fat screwdriver will not work. Now let's get started with assembling of the motor base. So you can grab yourself your Phillips number 2 screwdriver here. I'll suggest you get yourself a little bit of a parts tray here so that you can set your screws up in such a way that you're going to have your M2 and your M2.5s nice and separated. Same thing with your motor horns. So go ahead and unbox all your servos at this point. Now the assembly process is the exact same, effectively, with a few caveats, with the follower and the leader. So I'm now going to assemble the follower. And I'm also going to make notes on, if you're assembling the leader, what kind of changes and differences that you're going to have to make to your design. So let's go ahead and grab our base design here. If you're using a follower, of course, they are all going to be the 1 to 345 ratio. If you're going to do the leader here, you should put in the 1 to 191 at this point. So with our servo, we have a black section in the back, which is kind of like an idler, as well as the actual servo motor horn there. So I'm going to go ahead and add a servo horn. This is the one that has the threaded 25 tooth spline. We're going to push that on. And on the other side, this one just press fits, just has a hole here with no threads. We're just going to press fit that on. So we end up with a free spinning idler on that side. In here, we're going to add in the larger machine screw. That's the one with the fine threads, the M2.5, and we'll put that through the center of our motor horn to be able to hold that servo in place. And now on the servo, there are 4 holes. Small holes. These are where our M2 screws are going to hold our motor in place. So we're going to slide this motor with the active part, the active side of the horn, in the center of our base here. Give it a good little click. And then in the bottom, there are 1, 2 mounting holes, and at the top, there are 1, 2 mounting holes. At this point, we're going to grab our Phillips number 1. We'll grab the small little wood screws and these M2.5 with the coarse threads, we'll screw it in here. Now what's important here is you don't want to over tighten these because we're just going into plastic. We're effectively self-tapping our own screws. So we don't want to over tighten these. Just get them good and finger snug. And then that's ready to rock. Now, the thing I like about this iFixit screwdriver is that at the back here, it has a rotating, so you can grab it and press it against your finger here, give it a little rotate with your fingers, and that makes it really easy to start putting these things in. Next up, we've got our motor holder for this bottom motor for the base, and this just slides on top like so. Make sure it's fully seated. And on each respective side, there is 1 and 2 mounting holes where we're going to put more of those small M2 screws in to be able to hold this motor base in like so. Next up, we're going to grab the motor base, and if you look on the design here, there's these little extra slit sections that makes it easy for us to slide up and over that screw. So I'm going to have the motor section facing up towards that base, and I'm going to want to try to line it up so these 4 holes here already in line with the 4 holes of my servo at this point. So I'm going to slide it through, slide over top, and I may need to give it a little rotation until I can get those sections lined up. Now I can grab those M2.5, swap back to my Phillips number 2, and we can start mounting these in like so. You might need a push to be able to fit it through, and I suggest you get the first one in just a little bit, then go cross over to the other side, put in the other one, and now you can fully tighten these ones in. Again, give these a good little snug. Doesn't have to crush these things because on this one, you're actually going in some aluminum, and it can actually be surprisingly easy to strip aluminum. Now on the back end, we'll check to make sure that we've actually lined up. Inside of our hole there, we can see that our holes are lined up. You can also use your screwdriver with the maybe Phillips number 1 tip, and you can give it a little twist so that these sections line up a little bit better for you in those threads. Again, we're going to use those M2.5 screws in here. So I'm going to put all 4 in. And rather than tightening down like crazy, I'm going to make sure that I put in the 2 edges first. Because what can happen is if you tighten one up all the way, you can actually end up losing some of those holes and you lose some of the tolerance. Now's a good time to check that we still are able to get full range of motion all the way through. In this case, we are. Sometimes what can happen is you've got to stop on your servo, and that can only spin around 360 or 350-ish degrees, one direction to the other direction, and there's a hard stop here. So what can happen sometimes is if you have been spinning the end here, you can actually hit your hard stop in the middle. If that happens, what I would do is I'd just take your section out, reset yourself back, and then check to make sure you still got full range of motion. In this case, we're good. Now next up, we've got our little motor base here. Now what we want to check is we want to make sure that our cable management is all on one side. So we've got this little cable management hole here, another cable management hole here. We'll slide that down like top, like so. Now for both the leader and the follower, you need a 1 to 345 motor here. And then because our cable management is going to be on this side, we're going to put the back of the servo with our servo motor ports there on this side, so we can go ahead and slide this around so the servo horn faces up. Go ahead and give this a good push in. And at this point, we can take our M2.5, or sorry, our M2 screws, and we have 1, 2, 3, 4 mounting holes. Now on the design here, one of these holes is actually enclosed, so we can only put in 3 for some strange reason. So we'll go ahead and mount in those 2 on this side, and then 2 on the other side with our M2.5s. Or sorry, not 2.5s, this is our M2 screws here. Put in 1 more, and this should have our motor now secured. Same deal, rinse and repeat. Grab that servo horn that does not have the threads, push it on like so. Grab the servo horn that does have the threads. We'll grab our 2.5 screw, oops, and our Phillips number 2, and we'll go ahead and mount this one in as well. Now here's where having a magnetic screwdriver really helps, so that these things don't come apart. Now we can grab our shoulder joint. It is the one that does not have the little small curved section. This one is our elbow, this one is our shoulder. And again, we want to have our cable management sections all up on the same side. So I'm going to slide this in. And on this one, we have to end up sliding it in from the top because that's where our slot is. And we're going to want to make sure that we have our holes lined up as we slide this down and on. You may need to expand this a little bit as you get it on, but that's okay. Give it a little rotation, and now with our holes lined up, we'll put in our 4 M2.5 screws on both sides. Again, I like to go corner to corner, just a good assembly practice to make sure that your holes line up. It's the number of times that I have assembled an arm together or a hardware component and it doesn't have these parts lining up. It can be a real right pain. Flip it over, and again, we need to maybe give it a little rotate to actually get that point. And you might find that your holes just don't want to line up as might presently are. So you may need to give it a little pick up. So what I'm doing is I actually pick this up while I give it a rotation to be able to make sure that I can line those holes up. And once you can get one started, generally the other ones come on in place. Again, I like to start one just a little bit before I fully seat the other screws down. Depending on the tolerance of your printer, you may need to push a little bit to be able to get these screw heads through as well. There we go. So now we've got the shoulder connected. Now for our elbow flex, again, on the follower, it's still going to be that 1 to 345. If you're going to be the leader here, this one needs to be your last 1 to 191. So this is the last motor we have to be concerned about that has a different section. Go ahead and slide it on like so that our active section is away from our cable management side. Again, we have 1, 2, 3, 4 holes that we can put our small M2 screws in. Just get a little snug. Reminder not to over tighten these. This arm does not have a lot of torque that's being applied to it, so you really don't have to go crazy here. We'll put in the side without the threads, give that a good little snap on, and the side with the threads as well, and then put on our M2.5. Oh, and while we're at it, we should actually check we still get full range of motion on our shoulder before we go too crazy. So our shoulder should be able to rotate all the way around and get hard or physically stopped and physically stopped again on each respective side. So as long as you can do that, you're good. You don't have to worry about centering your servos. It's not a huge deal. Next up, we need our elbow joint, which is the other side of this. And then our elbow joint should go like so, with the other arm facing up. We will press this on, give it a line up, and then we'll put in our M2.5 screws again. Make sure you've got those screw holes lined up. Sound like a bit of a broken record on that, but it is. You only have to do it once to understand my pain. And I also understand your pain if you have to go back and redo this as well. We'll flip it over. Again, you'll see that my holes are not lining up, so I might have to give it a little flex out as I rotate. And as I'm flexing around that, we should be able to rotate those sections on like so. So let's get one of those in. And the other corner in. There we go. Beautiful. Just two more. Okay. Again, let's check our elbow flexion here. We should end up getting hard stopped by the edge of this elbow here. As you flip around, we should end up getting hard stopped. Just verifying we don't get hard stopped in the middle. At this point, we're ready to do our wrist flex at the end of our elbow. So we're going to take a look to make sure we have our cable management slots and the other motor base holder with the cable management slot. We're again going to slide this on like so. And we will have the active part of the servo facing the other side down like so. Oh, sorry, I forgot to mention. For the leader, this one should be 1 to 141, and then for the follower, of course, is 345. Now for the leader, the last all three motors in the wrists are all 1 to 141s. So we push this in. We have 1, 2, 3, and 4 holes for those M2 screws. So let's go ahead and mount this servo in like so. And this will be our wrist flex servo. So this is the part that will actually tilt our wrist up and down. Now, before we go any further, well, actually, let's get the servo horn on and then we'll talk about that. So we'll get that servo horn on with the teeth on like so. Give it a good little press, and we need our M2.5 to be able to do that. On the other side, we need to put our little idler. Now, before I go any further on this one, now we're actually going to put this to the side for now because we're actually going to assemble the wrist. Now, with the wrist, we have to take our either 345 for our follower or 141 for our leader. And we're going to slide the active side of our servo horn through on this half. We'll go ahead and slide this all the way through. Really got to give it a good little snug to make sure it's all the way and clean. And we'll go ahead and mount our servo horn on with the teeth spline. Put this in with our M2.5 screw. And then we have 1, 2 screws to be able to hold this one in. So we'll put in 2 of our M2.5s for our wrist. Now, before we mount the wrist on, like so, we're actually going to put in 2 of those cables. Now, we've got a 3-pin connector here, and this 3-pin connector is keyed. So you can see that there is only one way that it's capable of going in to these. It does not matter which port you send these to. These ports are little daisy chain ports. So effectively, this cable here, white is our signal wire, red is our power or our 5 volt or 12 volt, depending which power supply using, and black is our ground. And these will only go into these white ports one way. So I have to set it up with the white port on the left. If I try to put it in like so, it's not going to fit. So with these ones, you just simply give it a little press, push it down, and now that is fully seated. So I'll grab in 2 of these, and I'm going to put in both of them. I find it's easier if I have to get my screwdriver to help push on the plastic section to help get that a good little snug in. And then same deal, making sure that I'm following that key, because we'll only go in one way. And now we've got both of these on here. Now the reason I'm doing this right now is because this can be a right pain to be able to cable manage in the end. So we're going to slide this on so that the end of the servo is facing this way on top. So let's mount that in like so. We'll line up our holes and we'll put in 2 of our M2.5s. Now you notice that on our wrist that we did not actually put one of the idler oh, can't get that one in. There we go. Now we did not put one of those idler horns on the other half of the servo. The wrist only requires the servo horn. So it's a bit of a pattern break compared to what it is that we've been doing up to this point. Go ahead and put the other 4. Oh, and conveniently, I managed to line this one up for the most part right away from the start. Make sure I'm actually using my M Phillips number 2, not my Phillips number 1. I'll mount the other 4, and we're just about done with the assembly process here. Oh, apologies for that camera shake. Okay. Now before we go further, we'll go ahead and do a check to make sure we still have that range of motion. We should bottom out on both sides of that. Again, if you bottomed out in the middle here as opposed to the end, you can just take your servo horn off, give it a little swap. Now here's where there's a bit of a pattern break on whether you're doing a follower or the leader. Up to this point, these arms are the exact same to here, aside from the motors themselves. Now for the leader, you're going to put the pistol grip on here at the bottom in such a way that it's facing on the bottom neutral, and then you have the little trigger that's going to be faced on top. On the follower is where you're going to be using the claw to be able to do this. Now for the follower, I like to set this up so that my camera is going to be facing sideways and the bottom section faces down below. So we will rotate it so we can line up our screw holes here and put in our M2.5s. So I'm going to give these a little twist in. This one can be a bit of a pain to get in just because of the angle. So you end up having to have your screwdriver on a slight angle. Now you can use the claw design that does not have the camera mount on here. I like to put the camera mount on this one because it just makes your training data just a little bit more accurate. Okay. Now on this one, we're going to check our rotation and motion. We're going to spin it around. And again, you should get 360 degrees. What you're really looking for is it doesn't really matter where the hard stop on this point is. You can see that as I rotate it around, I get a hard stop on this section, or I get a hard stop on this section. It just depends on where your arm is going to give out on its position. So whether you turn to the left or right. You probably wouldn't want it to give out in a bit of an awkward angle though. So you can probably change that servo arm around. Now we're on to that final motor, which is of course our 141 on the leader or the 345 on the follower. We'll go ahead and slide those in, pop in our M2.5. Now on this one here, you want the active side facing to the right or where your other servo is, and it should slide right in like so. And then we have 1, 2, 3, 4. Sorry. And then we have 1, 2, and 3, 4 M2.5 screws respectively. So let's go ahead and put those final 2.5 screws in. I'm going to Now, if you're wondering, there are 2 extra little mounting holes here. That is for a different camera design than this one that is 3D printed. You could print one off later and add it on after. So now, of course, our claw can really only go on one way. We want it to be grippy together. So we'll slide this in from the top. And we will put in our last 4 M2.5 screws. Well, not the last 4, the last 8 M2.5 screws. Oh, I didn't follow my own advice on that one, and I couldn't line those up because I tightened that one down all the way. That'll get a little snug. And let's do the other side. Line up our holes. And our last 4 screws can now go in here. Okay, and that's it. We are now all assembled. We'll do one last claw range of motion here, and we're good. Now at this point, if you still need to assemble your leader, you can go back through, watch this video again, and then, or watch this section of the video again to be able to assemble your leader. So before moving on, you should have both your leader and your follower set up. So before we can actually continue with the training, we have to be able to let our motor controller know and our computer know which motor is which. By default, I believe these come programmed as motor 1. So because what we're going to do to power these is this servo is going to get connected to this one gets connected to this, and so on all the way down the chain. Because those servos have 2 ports on them, one allows it to both supply power and transfer signal to another servo further down the line. It's called daisy chaining these things together. So we need to let our computer know and our motor controller know which motor is which. Now the nice thing is you only have to do this once because it actually gets saved to the firmware on the motor itself. So we're actually going to go ahead and plug in a single cable to each of these motors. So up at our gripper section here, we're going to go ahead and connect this in. Now, it does not matter whether you connect this in left or right, but what I would suggest that you do, again, I like to use this little Phillips screwdriver here on the pushing on the plastic to be able to get these things in. I'd suggest that you do any section where you're going to be providing power to the motor on the left and then daisy chaining on the right, or the other way around. It doesn't actually matter which way you do this, but I'm going to supply power to the motor on the left, and the one that's going to supply that daisy chain connection should be coming in. So you can think of it as input and output on the right. Now we don't have to connect 2 to this one because I already connect 2 cables. We're going to go ahead and connect 1 to this motor down below. And again, I'm going to always plug these ones in on the left just because it makes life a little bit easier. And we're going to end up with one motor that's not going to have a cable plugged into it at this point, and that's okay because we will swap it around later. Reason being is that it just makes it so, oh, I had that backwards for that key. Just makes it so much easier for us to connect these things later. And it's not going to affect this because we'll change that wiring as we go. There we go. So with all of those wires connected, again, this bottom shoulder pan is not connected right now, but we'll get to that as time goes by. So don't worry about that right now. Now, before we get to that wiring, or before we get to actually assigning it, we have to put our motor control board on. So I'm going to grab my little wave share connector here to the back of my motor. And yet with these little brass standoffs to the back of this motor controller, so we're going to put those brass standoff on the back like so. And we'll grab our Phillips number 1. And we'll mount through our wave share motor controller into that brass standoff. Wait. It's falling on me. Let's try that again. I'll mount into that little brass standoff, and we'll do that on all 4 corners because this ends up just being a press fit into our motor controller port. Does not matter which side you end up pressing it in on, just so we have a connection point on this motor controller. And it stays connected to our robot. Okay, so now we've got that pressed on like so. On the opposite side, we have this little tab. We can go ahead and line up these sections and push them down and in. You may find it easier to take a screwdriver to give you a little push into each of those corners till you set yourself down. And now we've got our motor controller in and pressed. Good connected, and this side just slides on the back like so. I'd suggest that you put the USB cable down on this with your motor controller facing up. And then to be able to connect to the computer, you simply plug in the USB-C cable here and the power supply here. You can repeat the same thing with your other robot arm, and let's get our training set up. All right, so let's take a look at my training stage here. Now, off camera, I have gone ahead and added in my claw to the camera mount here, as well as I have my additional webcam up on my post so that I end up with a consistent staging area. Now, one thing that's important to note about my training area here is I have a separate location for the follower for the leader, and a different location for the follower. Now, the follower's arm is capable of seeing and reaching in a section on just about every point of this table. And my table is a nice flat surface with no other details on it. Because we're going to be using vision models to be able to train these arms, we don't want a very busy table surface. So if you can, try to get yourself a solid color surface. It's going to make your life a little bit easier. Looking at the back end of each of our robot arms, I've taken my clamp and I've clamped this down to the table. I've put my motor controller on with the servo ports facing up, as well as I have this connected via the USB-C and the power supply for our motor controller. Now, one thing that most people find is that running through a USB hub is not great. If you can straight connect this to your computer, it is better than running through a hub. So now let's head on over to the computer so that we can actually do some of that initial setup. So now that you have your robot arm set up and initially wired, but not configured yet, we need to get our environment set up to be able to actually have the Hugging Face LeRobot repo on our computer. Basically, this gives us all the commands that actually let us run that LeRobot. Now, the first thing we need to do is we need to get conda set up, and we're specifically using Miniforge to be able to set up that conda. So if you don't know what conda is, conda allows you to set up something called a virtual environment on your computer. So we don't want to program on the main root folder or all of our main files are stored on our computer, because that would end up making things a bit of a mess. For instance, when you have things set up in your document folder, you have your docs folder, you might have music, you might have pictures, and so on. So what conda lets you do is it lets you make virtual environments. You think of it kind of like setting up your workspace. You can say, hey, conda, make me a new workspace. So it makes you a new blank empty table. Then you can start installing and working and moving things around on. So we'll make ourselves an empty table for the LeRobot repository. Now, if you already have conda installed, we can go on a little bit further. If you don't have conda set up, if you go on to any internet browser and you search for conda Miniforge, you should be able to find the conda-forge/Miniforge setup. It's kind of a lightweight version of a conda forge. And we need to be able to install this. Now, there's a few different ways that we can install this and actually get it set up. If you are on Windows, there's a specific Windows installer that you can follow. If you are on Linux, there are specific terms that you can grab, either wget or curl. It depends on what you have set up. Likely, you're going to have to use curl if you're going to be using macOS. So this is what I'm going to grab. So I'm going to grab this. I'm just going to copy this. And effectively, what this command is going to do is it's going to download the conda Miniforge program or onto our computer. You can also do this as a installer if you want to. I believe they have full packages with macOS. So you could also download either the package installer for Apple OS or Intel. That's kind of like the one where you do your drag and drop. But I'm going to do this from the terminal window, because for the vast majority of this tutorial, we're going to be running things from terminal. So if I do Command space, I can open my search and I can open up a terminal window. And inside my terminal window, I'm simply going to copy and paste that command that was given to me here underneath this Unix-like platform. And it's going to take some time to be able to download all of this conda mini-forge work. Now, once you have it downloaded, it's time to actually go ahead and install that as well. I'll zoom in a little bit so you can see a little bit better here. So now that it actually is downloaded, we need to install. So now we can run this script down below to do bash miniforge3, which will get our username. And then we will put this in as well. So this is going to go through, you can read our license and review. We can press enter to be able to make sure we actually read this license. This is pretty standard stuff. And yes, we agree to the license terms. We can press return to be able to go through that. It's now going to be installed at users bprat and miniforge3. This is an okay place. I would just use the default location. So you can go ahead and press enter to confirm that location. It's going to unpack it, and it's going to install all of this conda files, everything it basically needs to be able to get conda and miniforge set up for you. Okay, so at this point, it's going to ask us, do you wish to update your shell profile to automatically initialize conda? Yes, you do want to. However, we want to copy this line here. Effectively, if we say no at this point, if we were to type in a command later where we were to say conda, which is going to let our Mac know that we want to run a conda-based command, it won't actually know what conda means. So we're going to type in yes and then press in return here so that it automatically sets up conda. The one annoying thing about this is this means that conda is permanently set up, and we don't actually want to have it permanently inside of our base mode instead. So now we're installed, we're ready to go. So now our conda set up, we can go ahead and close down our terminal and open up a new terminal window. Once we open up a new one, we're going to put in that conda config, set auto activate base to false, so that we don't set up in that base every time. Now at this point, conda miniforge is now set up, and we can continue with actually setting up our LeRobot environment. Now we need to make a main directory for where our repo for the LeRobot is going to be set up. So I'm going to go into my Finder window, and I'm coming into my documents, and I'm going to go in my GitHub folder. And in here, I'm going to make a new directory. I'm going to call this one LeRobot. And then up here in our terminal, we can type in the word CD, which stands for change directory, and we can just simply drag and drop our LeRobot in, and we'll automatically set up where our path name is. You can also right-click on any folder, hold Alt, and instead of copying the folder, you can copy LeRobot as a path name, and it will do the same thing. So now that we are in the correct repo, we can now start setting up our LeRobot environment from here. So one thing that can be really helpful writing through this, so you don't have to type this through as I'm going through. If you go to huggingface.co/docs/relobot/installation, we can actually copy and paste some of these commands in for us. So we've just installed conda miniforge, and then we are change our directory into where we want our LeRobot to actually go. And now we're going to create that virtual environment. Remember that kind of empty table for us. So we're going to grab this conda create yes no LeRobot and Python 3.12, and it will create a conda virtual environment for us. It's going to take a little bit of time to be able to set this up. It's got to download a few more pieces for us. And at this point, we've created that environment. And in order to be able to access that environment, right now you can see that we're just in our main base section here. So what I can say is I can say conda activate LeRobot. And you'll now notice that I'm now inside this LeRobot virtual environment. So any changes I make are going to be to that virtual environment inside of that LeRobot directory. If you ever want to get out of your conda LeRobot, you can either just close your terminal, or you can say conda deactivate, activate, and it will get you out of that LeRobot. Now I'm going to press up on my arrow keys to be able to select the previous command I was, because I actually want to activate the LeRobot to actually be inside. Now, in order for our camera system to work, we need to make sure we install our FFmpeg format here. So we will go ahead and do that by grabbing this conda install ffmpeg-c and then conda forge to be able to install that. So we'll go ahead and copy that, paste that in. It will then grab from conda forge our specific FFmpeg module. So I will proceed with Y and press return, and it's going to go ahead and download, as well as start installing some of these FFmpeg translators for us. Now that we've got FFmpeg, we can verify it's installed by doing ffmpeg-version to see what version we are running at. And we see that we are running 8.0.1. So at least at the time of this recording, any 8.x version is actually not supported. So instead, we're going to grab this conda install ffmpeg 7.1.1 to make sure we actually grab that ffmpeg. So I'm going to go ahead and paste in conda install ffmpeg 7.1.1-c and then conda forge, and this will actually write over our version of ffmpeg. So we don't have to actually uninstall it, we can just write over it. So we will proceed because this is actually going to work with our LeRobot. And now we can do that one more verification again. We'll do ffmpeg-version. We'll verify that we are at least running on a 7.x version. And we can see here that our ffmpeg version is 7.1.1. So now we need to actually clone that repository. So we're going to have this git clone. And then because we're already in the LeRobot directory, at the very end of our git clone, we'll add a space and we'll put in a dot. And that will basically just tell our git clone to, hey, you should add the files inside our current LeRobot version folder, as opposed to creating a new folder inside. If you don't put that space dot in there, what'll end up happening is you'll end up creating a directory called github, LeRobot, and then all of the parts that you need. But because we put in that period there, it should just be dumping in all those objects. Now, depending on how fast your internet is, this may take longer, it may take shorter. Again, I'm probably going to speed this up to be able to show you what this looks like when it's done and actually fully installed. Okay, so at that point, our Git repo is now done. So if I were to go back to my folder and go inside LeRobot, you now notice that we have all of our parts that we need. Now we're just about done with setting up our environment. We do not have to actually change the directory because we're already in there. The last thing we need to do is we need to install that library in editable mode. So I'm going to say pip install-e and then a dot as well to make sure we're in that correct directory as well. And this is going to grab any sort of dependencies that we're going to need, things like we need for our motor controllers, things like we need for looking at cameras, things like we need for running those different AI training tools, and so on and so forth. This is going to make all those dependencies to make sure that everything that we are running on actually works the way we would expect. So it's going to do a bunch of different downloading of a bunch of different libraries and so on so that we can actually get this thing set up and ready to rock. So again, this is going to take a while depending on how fast your computer is. So we're going to go ahead and how fast your internet is. So I'll probably speed this up to show you through at more speed. Coming into error here because I forgot to install the FETech library. So I'm going to say pip install LeRobot FETech. We'll go ahead and run that, and it's going to install in the library. So now that your computer's environment is all set up, it's now time to start with the actual teleoperation. So what teleoperation or telecommunications operation means is that you are effectively taking one hand, whenever you move it, the other hand will follow exactly as you want. So you have a leader arm and a follower arm. In the old days, it used to be called a master and a slave arm, but now the proper terminology is a leader arm and a follower arm. Sometimes people call the leader a teacher as well. So you have one arm that is teaching or leading, and the other arm is following exactly what it is that you are doing. Now, at this point, rather than using the official docs, I have taken the official docs and I've making them a little bit more clear for you in a companion notebook instead. I find this is a little bit more beginner friendly because the official documentation causes us to have to jump through at this point to about 4 or 5 or 6 different links. and information is hidden in a flow that I find is not very useful for beginners learning how to do this. So if you want access to this notebook, you can take a look in the description down below, and you can join my community down for that. Of course, you can still follow through this tutorial completely, even without this notebook, because you can just copy and paste things as I go. The reason I like using this is it's a really convenient place for me to be able to keep track of all of my notes. Using that Colab, it tells me when I have to throw things into terminal and so on, and things like that. As well, it also auto completes some different commands for us. So the first thing we need to do with my notebook is inside this helper setup, every single time we need to run this command here. And in Google Colab, if you don't know, effectively we have some text-based boxes, and then we also have some code that we can run. So I'm going to go ahead and click play on this, and it's going to run this code here. It says my helper's ready. I can fill in any configuration cells as I go throughout the tutorial. So as I'm running through this tutorial, every time I come back to Colab, if I'm coming back to a later date, I have to make sure that I run this config file so that it can help up with our little helper function. Now we've already done section 1 for environment setup, so we can go ahead and close that up with this little drop arrow right here. And then now it's time to actually do that robot calibration and that setup. So at this point, you have to make sure that you have your robot controller plugged in your computer via USB-C. You have to make sure that your motor power supply is plugged into your motor controller for both robot arms, and then the USB is plugged into your computer as well. Do not forget to actually plug it into your computer. Now, it's important to note that your USB ports can change, and depending on which operating system you're running, they might look a little bit different. So for instance, on a Mac, you might have this dev TTS modem. On a Liv, you might have dev TT USB or ACM. And on Windows, you might have COM3, COM4, and so on. Now, for most users as well, and Windows particularly, if you unplug your motor controller at any point and then plug it back into your computer, you might find that these COM ports or those USB ports change on your serial bus. So you might need to do that. So what we're going to do now is we're going to go ahead and open back up our terminal. And for me, I'm filming this on another day, so I'm coming back to it. So I'm going to go ahead and do change directory. And I'll come back and I'm going to load back in the directory that I want to change to. And then I'm going to do conda activate LeRobot to make sure that I'm inside my conda environment. If you've been following through up to this point, you're already there, but that's how you can get back into your conda environment if you happen to have closed off. And then here, we're going to run our LeRobot find port. So I can go ahead and copy this command. As a note, anytime you see this inside of the notebook here, anytime you see this little computer symbol, means you're running things in your terminal, not on the Colab notebook itself. So I'm going to select LeRobot find port. Go ahead and paste that in, and it's going to list all of the serial ports that exist for me on my computer at the moment. You can notice that there are a lot of different serial ports currently connected on my Mac. What it's going to ask you to do is going to ask you to remove a USB cable. So I'm actually go around to where I had my USB connected to my arms, and I'm going to do my leader first. So I'm going to clear myself around. I'm going to unplug the USB cable on my leader. Once I've unplugged it, I can press return, and you'll notice it'll tell me what my port is. So at this point, I can plug it back in, and we'll see what that port was. It looks like it is the dev TTY. So I'm going to go ahead and copy this. I'll Command C to copy that. And then inside of the next config file here, we're going to paste this in between our string here so that we can put it in for our leader port. So for me, it's going to be my USB modem, 5A, and then a long string hash. Now I'm going to do the exact same thing again, but for my follower. So on terminal, once I have a blank command, I can simply press the up arrow key, and it will remember the last command that I just typed into terminal. I'll press return again, and now I'm going to walk over to my follower arm, and I'm going to unplug the USB-C cable from my follower arm, press enter, or return, and then plug it back in. And we now have our other motor bus for our follower. So I'm going to go ahead and copy that over as well with Command C, and we'll paste that in as well for our follower. And then I'm going to press the play to be able to save those ports into our config file. Now, what this little config helper tool does is it stops us from having to type in our specific modems every single time we set this up. So if you're on Windows and you're on a different COM port, the next time you come back to this, simply replace your USB ports here inside of your config port, and then you're ready and off to the races again. Now it's time to actually do our motor setup. So at this point in time, with your follower arm, when you get the servo arm, every servo arm has a default ID number or an identification number, and they're always with a default ID of 1. If you remember on the arm, we took one servo motor, we plugged in the next one, we daisy chained it to the next one, we daisy chained it to the next one, and so on and so forth. We need some way for our motor controller and our computer to know that these are different motors, because presently it thinks that every single one is ID number 1. So we're now going to run a command here to be able to set the different default IDs for each motor. So what we're going to do is we're going to run a specific command, and we're going to connect each motor one at a time to our control board. And then LeRobot will tell us which one we should sequentially actually plug in. So I'm going to go ahead and play this in. And the nice thing is it's automatically filled in my port that I need for the LeRobot arm. Now, if you're on Mac and Linux, you can go ahead and just copy this command here. If you're on Windows, you cannot have any line breaks in any of your commands. That's what this little backslash is doing, is that this allows us to have a line break and it keeps code a little bit cleaner. But on a Windows computer, it doesn't work if you do that. So you're going to have to copy this whole line and do it all as a single line. Now, if you're not using my notebook, all you have to do is just make sure that you are typing in your robotport.dev.tty or whatever your COM port is. I suggest you have some sort of note or something like that to be able to put these in. But this is the command that we are actually going to run. And let's go ahead and put that in and press return. So now we can actually start following through where it's going to ask us to connect the controller board to the gripper motor only and then press enter. So I'm going to find the gripper motor. Actually, I'm going to unplug my webcam here so that we don't have this thing running all over us. And on my gripper motor, which is this one up here, I'll grab this individual wire. I'm going to plug it into either port of the motor controller. It does not matter which port you plug it in. Once I have that, I can come back to the terminal, press enter. It's just set the motor ID to 6. So now it's going to ask me to go to the wrist roll. So I can go ahead and unplug this now. I'm not going to plug it in yet. Now the wrist roll is the one that is actually doing this section. So this is the one we plugged 2 wires into earlier. Nice thing about this is that now we don't have to fight with which one. You can choose either cable. It does not matter. Come back into our terminal, press enter, and that is our wrist roll. Now it's going to come back to our wrist flex, which is this one here, and we have that cable already plugged in. So I'm going to grab this wrist flexed, press enter. Now it's going to ask us to do our elbow flex, which our elbow flex is this one back here, which is the next one on that line. So we'll grab that cable, we'll plug it in to our port here, and then press enter. Now it wants us to do our shoulder lift, and the shoulder lift is this one up over here. So I'll grab this cable, we'll plug that in, we'll press enter. And now it wants us to do the shoulder pan. So I can unplug this cable. And I'm actually going to go back to where I had the gripper originally. I'm going to unplug this cable from the gripper. And we'll plug this cable into the shoulder pan down on the bottom section here under that shoulder pan. Again, you may find that grabbing a screwdriver helps make your life a little bit easier to be able to actually push this in. So I'm going to grab a screwdriver to allow myself to actually push this in a little bit easier. Again, make sure you're pushing in from the plastic, and then we'll plug this shoulder pan in at that last section on the motor controller, and then press enter. And now we have all of our motor baud points set. So now let's actually go ahead and finish wiring up our robot now. So I'm going to unplug this guy. And now we can actually do our full daisy chains. Now my left is always going to be my output and my right is always going to be my input. So when I come up to my gripper cable and go from my left, which is my output, come into my gripper arm on the other side, and my right is my input. So I'm going to come around here and I'll go into the right on the input and make sure that I have that keyed correctly. And I'll grab my screwdriver to be able to push that back in because it can be a bit of a pain. And I'm also going to feed this underneath my wrist here through this little hole. And we'll plug that in now. Give it a little push, and there we go. That's now seated. Now on this wrist roll, we do have the ability to run through a cable management slot. So I'm going to slide this cable through into this cable management. You might find that having a screwdriver to help you push through that can help. Just make sure you don't pierce that vinyl coating. And we'll do a quick check to make sure that we have a full range of motion here. And we do have a full range of motion, so we're good. So now we can come out of our wrist roll to our wrist flex. So we can come from that wrist roll, coming out, and this one goes directly into the wrist flex down below. That one's got to be flipped around, and we will give that a little push to get that in. Make sure you're doing this nice and straight. Now on this side, we'll go through our cable management hole, through our next cable management hole, and we'll push that wrist flex into our, or this is the wrist, into our elbow flex. Make sure we push that one in. And then we'll come down again. We'll go through our elbow to our shoulder. Make sure you don't push through the vinyl casing because these things can be relatively small or slim. We will plug that in again, down there like so. And then the second last one, we'll go through our cable management holes again. Sometimes you can find as cable management, you can give it a little push and a twist through, and that'll make it a little easier. And we are going to come through, again, through our cable management hole here, and then up underneath, and into our last connection over here with the shoulder pan. Give this a plug in. We can fully close that up. And then for our shoulder pan, we're going to run our cable through this hole, through that last cable management hole up at the top here. This one can be a bit of a pain to get in, I would say. So sometimes I just skip it, to be perfectly honest. And then we can plug this into the top of our motor controller board. And then this motor controller board simply slides on the back, like so. So now we've got a fully wired up board. We can go ahead and clamp this down back at the back again, and we'll repeat the same thing with our leader arm. So now we're going to do the exact same process for our leader arm. Now, the thing to notice here is that the leader arm does have a slightly different command here. So again, I'm going to click this little play to show the command, and it's going to automatically fill in the port for our leader arm. Now you notice that unlike the follower, where we had our teleop type was SO101 underscore follower, it is now SO101 underscore leader. So I'm going to go ahead and copy this line. We'll go ahead and paste it into our terminal. And this might take a little while depending on how fast your computer is. Mine is not the fastest in the world, so it does take a hot minute for that to actually pop up. So we'll go through the same process again, where we're going to go to the gripper section. So I'll grab that loose cable I had, plug it into the gripper, give it a full seat. Then we can plug it into our motor controller, head back to our computer, and then we can press enter. It's going to ask us to do the same thing, but now we'll do the wrist roll. So I can go ahead and unplug this. I'll go into that wrist roll where I remember I had that double cable plugged in. Grab that wrist roll, press enter. Oops, not on the terminal. Press enter. we're good. We'll come back to the wrist flex, which is of course this one that flexes up and down. And we will grab that one. We will press enter. And we're good there. Now we're going to come up to the elbow flex, which is the next one in the line, which is this guy here. And my elbow flex cable is down here. Press enter. Oops, and enter. I'll come down to our shoulder lift, which is the next one in line, which is this guy here. And my shoulder lift is coming all the way back over here. Press enter. And then the last one is the shoulder pan, which to do our shoulder pan, I'm going to disconnect the one we used for our gripper. Plug this one into our shoulder pan all the way down below. And then we will again press enter as per usual. I like to use my slot screwdriver to help seat that. Plug in our last one, press enter. And now all of our motor connections are set up correctly. So same deal now, we can go through and do the rest of our cable management. So I'll make sure that my right is always my input. So I'm going to plug in and simply do my daisy chaining and go through any of these different cable management holes. So I now have my gripper plugged into my wrist roll. My wrist roll needs to get plugged into my wrist flex, like so. Now my wrist flex has to go into my elbow. So I'll plug that in. Then my elbow goes into my shoulder. Sometimes these things can be a bit of a pain to get sorted, that's okay. Then my shoulder has to come down, again, through that little gap into my shoulder pan. And then the last one is the actual shoulder pan back to that motor controller. We'll go again through that little hole into that cable management slot. This one was a bit of a pain, this cable management, so sometimes I skip it. And then we go into our motor controller. Finally, again, doesn't matter which port you choose. And we'll set it back up so that the USB cables are facing down. And now we can go ahead and clamp this. So looking at the current state of the world, I now have both of my follower and my leader and my follower arm clamped down. They're placed down beside each other. We're back to the original setup that we were at before this tutorial started. So I will set that up so we can see where things are going. So now that each motor understands its individual ID, and we can now say that, okay, ID number 6 is the gripper, and 5 and 4 all the way down to 1 for the shoulder pan as it goes, it's time to actually calibrate that arm. And what calibration means is right now, your arm does not know what its endpoints are and what its range of motion is. Because these are 360-degree servos, they would expect that they can go in 360 degrees, but that's not always the case because you, of course, have physical stops where these things are not able to go to. So we're going to now teach our individual arms what its start and their stop points are, respectively. Now, this is one of the most common ways that training can fail is if you have bad calibration for the arms. We say a lot in robotics, garbage in, garbage out. So if you put in a garbage input, you're going to get a garbage output. So make sure you're really taking the time to make sure these things are set up. Now, before we get started on this, it's time to actually go ahead and pick a name for your arm. So you can leave it as follower arm and leader arm if you want to. I'm going to say my follower arm is going to be red and my leader arm is going to be black for mine. If I run my config file, I've now saved these arms to that config script for us. And now it's time to actually do the calibration. So what is going to happen is we're going to run this command inside of our LeRobot terminal. And then we're going to move our arm to a specific point. And we're going to take every single joint and we're going to move it through its full range of motion. So I will copy my command, go into my terminal, paste it in, and we'll start the calibration process. Now again, some of these things take a hot minute to get up. My computer's not the fastest. So now it's asking us to running calibration of the follower arm, red SO follower, and then move the arm to the middle of its range of motion and then press enter. So what I want to do is I want to move the arm, and I want to move most of the joints to the midpoint of their range of motion. In this case, this is about the midpoint. Your midpoint doesn't have to be exact, as you can see, but it is more of a close enough kind of deal. So we'll come back, and now we'll press enter, and it's going to ask us to move each individual joint. I'll move my terminal up so you guys can see that. And now we really want to watch down here. So now I'm going to move each individual joint, except for the wrist roll, through its individual motions. So I'm going to move my gripper all the way up and all the way down. And you notice that it's now changing those minimum positions and the maximum positions that is able to move to. Next, I will do my wrist flex up and down. And then we'll do the same thing with our elbow flex up and down. Now the key thing here is you want to make sure you're really only moving one joint at a time. You don't want to be moving multiple joints. Now we'll do a shoulder up, and I'll pause. I'll lift my arm all the way up, and then we'll come all the way down. Now at this point, I'm going to move it all the way back to rest so that I can do that shoulder pan. So I find life a lot easier to do when it is back at rest. And there is the minimum and maximum points that it can go to. At this point, I head back to terminal, press return, and those are all of my joints calibrated. Now we'll go and do the same thing for our leader. So I'm going to come down to the leader arm. Again, we'll click this little play command so we can get an easy command that has our leader already pre-filled, our port already pre-filled, and our leader ID pre-filled. So we'll go ahead and copy this, go over to the terminal. We'll run the same command on our leader now. Now, once you calibrate the first time, it saves these to your LeRobot folder on your computer, so you don't have to worry about doing these things again. I'm actually going to have to move my computer out of the way to be able to do my leader arm because I've got a lot of stuff going on my arm here. And let's change our camera angle so that we can see our leader arm. And we're going to do the exact same process again. So I'm going to move this to its midpoint of its range. We will now press return. Oh, make sure I actually click into my terminal, press return, and we'll do the same thing. We'll move through the gripper all the way up and down. We'll move the wrist flex all the way up and down. Move the elbow flex all the way up and down. We'll do the shoulder pan, or sorry, the shoulder joint all the way up and down. And then I'll fully close my arm and we'll do our shoulder pan all the way around. We'll return to rest, and then we'll press enter. And now we've saved our calibration info. Now comes time to actually get to the fun part of our tutorial where we can actually have our robot arm finally move. We've done our setup with our IDs, we've done our wiring, we've done our building, and this is where things are finally going to feel like they're going to start paying off for you. It takes a while to get there, but it is going to start feeling really good. So now we can actually drive them. So what we're going to do is in section 3, we're going to start actually do some teleoperation and start adding in some cameras to get ready to do some training. Now, a basic teleoperation, it's always good to run a systems check. So what we're going to do is we're actually going to run a basic teleop where we'll have the entire arm running through in this motion. What we're looking for is looking for smooth motion, and we're not looking for any jitter or any lag in that follower arm doing what our leader is doing here. So let's go ahead and run our command here for our basic teleoperation with no cameras. In fact, what we're now doing is running the teleoperate method. We've already seen these before, where you have your robot type, which is your follower, your port, which is your USB, and then the robot ID, and the same thing with leader, and all the way back to the other sections on the leader as well. So I'm going to copy this over. We'll paste it into our terminal. And this one takes a hot minute. Let's go ahead and open up the other camera so we can see what it is that we're looking at. And let's take a good look at our whole port here. So you notice that my teleop loop time is now 16 milliseconds. It's a little bit slower than typical because I'm, of course, adding recording to this. I have a lot of things open. If your loop time is really a lot slower than this, you probably want to try closing down some extra apps, things like Google Drive, things like Google Chrome, whatever other apps you're running, just to free up some memory. So now you notice that as we actually start to rotate this, and let's actually take a look at the whole iPhone here. So as I rotate my arm, my follower is now doing exactly what my leader wants to do. As I move up, as I move down, and we want to check that all of these joints are indeed moving the way that we would expect. Does my gripper actually move all the way up to its full position? Does it actually rotate? Can I actually reach that full range of motion? Are there portions in time where my arm is no longer able to actually pick things up? And what is fun now that I like to try in this first teleop is grab your first object and see if you can actually cause your robot arm to pick it up. Because, oh, I need to get a little bit lower there. Because you should be able to celebrate some of your successes that are going on because you now have a fully teleoperational arm. At this point, I usually pause and just muck around with my arm a little bit. You can see just how quickly you're able to get your arm going. You'll notice that because of that loop time, depending on if you do things too quickly, you can see where we just had a crash there where it's no longer able to read its position because we're going too quickly. So if that does happen, you can just press the up arrow, run your same command again. Make sure you start yourself from that base position and move slowly with your robot arm. Try not to move too quickly. You notice that our arm just snapped back really quickly because it's trying to match the arm. But slow, controlled motions are better because, as you can see, you can definitely crash things out by trying to go a little bit too fast. Now, when you want to exit this command, on a Mac, on a Windows, on a Linux, doesn't matter. Click on your terminal, hold Control-C. And Control-C is an escape command that we can run. And yes, typically on Mac, you do press Command, but in this case, you actually only want to press Control-C to be able to disconnect that arm. And you can verify things are disconnected by moving your arm around. It won't actually be moving up at that point. So I hope you get some celebration on that you have that set up. Now with the basic teleoperations setup done, it's now time to actually set up our cameras. And this is probably the most dependent one on whether you're using an operating system for Mac, for Windows, or for Linux. So let's take a look. Now, LeRobot uses OpenCV. If you have yourself a Intel RealSense camera, you have slightly different ways of setting this up, where you should take a look at the official camera docs to be able to see how you do the Intel RealSense. But if you just have a standard webcam, we need to figure out which index numbers we actually need for that. So, inside of our terminal, we're going to run the command LeRobot-find-cameras and then space OpenCV. So let's go into our terminal. We will run that LeRobot find cameras OpenCV. And what's going to happen is we're going to get a whole bunch of cameras showing up. I presently have 1, 2, 3, 4, 5 webcams connected to my computer. And what it's going to attempt to do is it's going to attempt to take a snapshot out of all of these. And some of mine are going to fail, partially because I am already doing recording on this. Hopefully yours does not do that. Mine gets a little bit funny when I show this in a tutorial context because, of course, I have OBS Studio running in the background with recording 2 separate cameras. So life does get a little bit funny. But what we can do now is what we would expect to see is we would expect to see that it has detected some cameras. Now it's going to say some things are out of bounds because I also have the continuity camera set up on my Mac OS as well. So I have camera 0, I have camera 1, camera 2, camera 3, and camera 4. And they all have slightly different widths and heights, different FPSs, different formats, and so on. Now, On Mac, this is the most restrictive. So let's figure out which cameras we actually need to be able to set up. So if I come into my main directory where I have my LeRobot, I should have a new top level folder here called Outputs and then called Captured Images. And if we look at those captured images, I can see that OpenCV 0, that's my continuity camera. That's the one that's actually filming my desktop right now. I also have OpenCV_1, that is my main camera that's looking at me. I have OpenCV_2, this is the actual webcam that I want to use for the robot arm. I have OpenCV4, which is the webcam on my laptop, and then the one that did not get captured is OpenCV3, and that is my claw cam itself. So I'm going to want to keep track of this data to be able to do this. So to be able to keep track of that, we can actually write this data in to our notebook here. So if I scroll down here, we can go into our camera config. Now I'm going to do two of these. So I have my top camera here, or your bird's eye view, whatever you want to call it. I'm going to keep it as my bird's eye. Now for me, my bird's eye camera, looking at that output was camera number 3. Or sorry, camera number 2 was my bird's eye camera that I actually wanted. So for that top level view, I'm going to put in my cam1 index is number 2. And then for Mac, you do have to put in the exact width and height and FPS profiles here. This is not the case for Linux. Now for Windows, sometimes you can go around and change some of these, sometimes you can't. But whatever gets returned here, for whatever reason, the Mac's AV Foundation, the way that it runs the webcams themselves is far more restrictive, so you have to put in the exact details here. Now for my claw, I'm also going to go ahead and put the same thing as well. My claw index, I'm actually going to leave at none for now, but I'm also going to leave a comment for 3 for later because we only want to test this one camera at the start, and I'll show you how to do 2 cameras later. But for now, put this information in, but leave it at none because we're not actually going to set up 2 cameras at the moment. We don't want to get things too complex right away at the start. And then it is 1600 by 1200, 1600 by 1200, and then the FPS is 5. Now that's actually probably not going to return that, but that's okay. Now for my camera rotation or camera rot, this is actually going to rotate your camera as well, and you might need to play with this a little bit. Now by default, your camera rotation should be 0 or null. That is okay. And then you can do 90, 270, 180 to be able to rotate by 90 degrees. And we'll talk about this. So I'm actually going to keep my camera rotation at 0 so I can show you one of these set up. Now, as I press play here, it's going to play our first camera config. And this is the whole command that we use for actually running our command. And for now, we're not going to run camera 2, and that's okay. So let's go ahead and let's do a teleoperation with cameras to make sure that these things are actually running. Now, there's going to be a new display that's going to be popping up on our computer and something called Rerun IO. And what Rerun does is effectively allows us to see all of the joint angles, all of the camera angles that we are filming within our tool and piece here. It's also going to be able to show most of that data. So we're going to run with a flag here called display data equals true to be able to run this. So let's run this show command, and we have a new thing added to our command. So it's LeRobot teleoperate again, and these 3 are the exact same. We now have a new line called robot.cameras, and this is a string with a JSON format for bird's eye, and then here is all of the information we need for that bird's eye camera. And then we have this information as well, which was also the same for a standard teleop. And then we have display data as true, and that's going to actually run that rerun. So let's grab this command here. Let's go ahead and paste it in on our LeRobot. And let's actually do a teleoperation with rerun running in the background and being able to move our arms as we would expect. Oh. And it crashed. And the reason it crashed right here is because OpenCV Camera 2 failed to set FPS 20. The actual is 30. So again, some things get a little bit funny because I am running a recording, but in that case, that just means I have to go back to my OpenCV Camera 2 on Mac. It needs to tell me that I need to set my FPS to 20. So I'll come back up to my main camera here, and I'll set my FPS to 30 because that's what it told me to do. I'll run my config file again, and then I'll run my show command again, and we'll notice that it automatically updated my FPS. So we'll grab that command one more time. We'll run this again. Again, that's more of a Mac funniness. On a Linux, you could choose your own width and height, and I suggest you actually choose a lower resolution if you can, because the higher the resolution, the worse your camera data is going to be, because you're really just taking a lot of unnecessary data here. So let's take a look at our rerun. So inside of our rerun IO, we now have our camera where we can see that top camera we're looking at. We can also see specific angles and specific angles we have for all of our different action and observation. So action is, of course, our main follower, and observation is the arm that we are observing, which is our leader. So now if I were to open up both here, as I move my arm here, we can see that our angles are now starting to shift, and we might need to go a little further into this data because I was a little farther out. At this point, look at my terminal. My loop time is still 16 milliseconds. We can see that when I start to move things around, some of my loop times really start to expand. But for the most part, I'm good now. So I can do Control-C to go ahead. Oops. I will do Control-C to do a break character. And now let's go back and run this again with a second camera. So I'm going to come back up, and I'm going to now have my index of 3 as opposed to none. And then we have a 16 by 12, and I know this is probably going to fail at 5 FPS because Mac is doing some funny return things for me, but I will build this a second time. We'll now run our second camera display. And we'll now notice that our cameras now has a bird's eye, and if we scroll over, it also has a claw as well. So let's go ahead and copy this command, go back into my terminal, paste it in, and we will get some of that data through. And again, this is probably going to throw some errors because our claw camera is probably not going to be correct. So let's take a look at that. And maybe it actually does. Oh yeah, there we go. So we have a timeout waiting for camera 3, and we'll just try that a second time because my USB ports are getting a little overloaded with doing so much recording on this. So we'll try it one more time, see if we can get that second camera up and running. Sometimes the OpenCV 3 does not like it. Yeah, so it's not liking that third camera today. So I will have to probably disconnect and reconnect that camera to be able to show it up. Yeah, and it's just not wanting to open up on that third camera for that timeout. It probably has to do with the fact that this is about a $2 camera I had laying around at the side. But that is okay. You can still do your training on a single camera, and I would suggest you do your training on 2 cameras, but a single camera is still okay, provided you are able to see all of the data at a time. So I'm going to go ahead, back up. If I needed to, I could rotate this 90 degrees. If you do rotate it on a Mac, you'll have to swap your width and your height because it does not like, it will not automatically swap it for you. So I'll go ahead and swap those, and I'm actually going to put it down back as none again and remind myself that it is actually index 3 when I'm ready. We'll build that one more time, and then we'll build this one more time as well so that we don't run into those issues. So how do we actually teach a robot arm how to do an action using some different AI tools? Well, the model that we're going to be training for is something called ACT, or an action chunking with transformers. And that's a whole whackload of stuff, but let's break it down. So imagine you're going to teach your child or a niece or a nephew, whatever have you, how to build a sandwich. You wouldn't tell them, well, first pick up your arm like this, rotate it like so, move it over the position, pick up a piece of bread, twist it around, and come back. No, you'd simply chunk a lot of those actions together, and you'd say, pick up the piece of bread. Or in this case, you'd simply say, pick up the ball. because we might be able to pick up this individual ball itself. And that's effectively what an action chunking is doing. You are chunking actions together. Now, the key difference here is that this is action chunking with transformers. Now, a transformer is kind of the same thing as something like GPT, or a generative pre-trained transformer. Yeah, so that's what GPT actually stands for. It's also very similar to things like Anthropic's Cloud, or, Sora AI, or whatever have you, if you're using Kimi or any other AI models. A lot of these are large language models that are generative pre-trained transformed models. We can do the same thing with this ACT training model. Now, this ACT training model comes out of Tony Zhao, Vikash Kumar, Sergey Levine, and Chelsea Finn out of Stanford University, UC Berkeley, and Meta in about 2003. There's a full paper that explains how they're actually able to do some of this data and their training as well at the following website. As well, there's a fantastic about hour-long video from Alexander Sora. Apologies if I named that wrong, Soiree, I'm not sure how to say that. But he also goes through and explains how Aloha and ACT actually works as a training model, and I'll give you the quick 5 minutes cliff notes on this as well. So how the ACT training model works is you teleoperate your arm, or you have an additional arm that you teleoperate, and you train a model, and you show an arm how to do these actions. While it's performed these actions, you have a camera or several cameras that are recording that action over and over and over and over again. So you might have 30, 40, 50 individual recordings of that action. Once you're done with 50, 100, or even 1,000 different recordings of that action, you then feed that action in that has all of the positions for that robot arm, and it says, these motors were at this specific angle, at this specific place in time. You then feed that into a transformer model, who then watches those videos back and they say, okay, yes, what is this model trying to do? And in our case, you might say, well, the model is trying to pick up the ball. So you feed it in a recording of you picking up a ball like so, and the transformer model says, okay, it looks to me like the goal of this is to be able to pick up this ball and place it into this box. So this transformer then learns to predict actions further ahead. So rather than performing individual motor angles, say one position at a time, it performs the next 50 actions at a time, or the next 50 next steps. So rather than moving from here and having to predict every single motor motion to be able to get over here, it says, if I'm here, I can want to get to here next, I can fill in the blanks to be able to move myself over to that position. So we move over, say, the next 50 joint positions instead of one joint position at a time. Now, we also added an additional piece of information to this, which is a VAE, which is a variational autoencoder. Now, what this does is this allows us to apply for the variance in some of that training data. Now, as humans, we are really, really good at being able to move these things around and verify if I picked it up from this position, or from this position, or from this position. Robots are not so good at that. They would expect it to be in the exact same angles every single time, but that's not always going to be the case. So that VAE, or that variable autoencoder, allows us to smooth out some of that variation in some of those positions. And then once you've done your teleoperational training, so you've moved the robot through with a leader arm, you've moved that follower arm, and then you've passed it in transformer and that VAE as well. Then when it comes time to actually infer your model, run it inference time, then that model actually predicts and chunks together what those actions are going to be able to complete your task. Now, the ACT model is a huge breakthrough in AI training models. And the reason for that is because we can do a lot of these really fine-trained training data on really small, cheap devices. I mean, these LeRobot arms, to be able to put a whole thing together, you're spending under €200 to be able to put this whole thing together, and to be able to get a model that is good enough to, say, even feed in a cable tie or tie shoelaces. That is incredible performance out of a really small amount of data set. Something like a 50 model data set gives you enough data to be able to pick up a ball and move it into a box, or be able to put a cable tie together. When you think about how long some of these things actually take and how expensive some of these other robot arms have been in manipulation in the past, it is absolutely mind-blowing what these people have been able to do with developing this ACT model. So now that you have your cameras set up, it is time to actually start doing some data collection and training. So the first thing you need to do is you need to sign into your Hugging Face account on your local one here. So if you have not made a Hugging Face account yet, you can go to huggingface.co, and it's going to ask me to confirm my settings here. And then inside here, it is time to make a new token. If you have not made a Hugging Face account, you can do it by huggingface.co, make a new account. And then once you've made a new account, you can go to /settings/tokens, and then we're going to create a new token. Now, we're not going to select fine-grained read. We want to select write. Fine-grained just allows you to turn on specific permissions for each specific token. In our case, we want to create a write. We'll give yourselves a token name, and I'm going to give this one a tutorial _ test _ token. We will create that token, and I'm now going to hide my screen so that you cannot see this specific access token that I have. And make sure that you copy this and do not lose it, because this is the only time you're ever going to see this token or the access token. If you don't have it anymore, you're going to have to go back and be able to rewrite that token in or make a new token, and that's totally okay. Now we'll come back into our terminal. So now that we have our token, it's time to come down. We'll paste our token in here. My screen is currently blurred, so you can't see my token. I'm going to do HF auth login, and it's going to ask me to put in my token here. At this point, I'm going to copy in my Hugging Face token, paste it in. It's not going to be visible while you print this in. And then, yes, you do want to add your token as a credential, and then it should tell you that you have now been activated with your token and a login is successful. If you want to double check who you are, you can say HF auth who am I, and it will tell you who it is that you are. So I've now confirmed that my user is Pratt and I'm ready to rock. Now, scrolling down past my token, we're now going to set up that config for the rest of our files. So our Hugging Face user, we can delete this Hugging Face username and put in our specific user. And then here's where you can go ahead and describe your task. Now, the first time we run this, we're going to run it as a test. So it's automatically going to add in test for you. If you're using my notebook, if you're not using my notebook, you should probably put in the _ test. So I'm going to say blue stress ball tutorial, because that's what it is that I'm going to be trying to pick up. I'm going to try to pick up this blue stress ball. And then you need to describe your task. And my task is going to be taking this blue stress ball and placing it inside of this box. Now, you want to make sure that your task is the same every time, particularly on your training, because of how the ACT training model works. So for describing our task, this is kind of like if you're using an AI prompt, you're just going to say what your task is. So I'm going to say, place the blue stress ball into the box. And that is my full prompt. You want to be nice and descriptive, but not too descriptive, as is what it is you're trying to do. Now, there are some other settings that we can run, things like number of encoder threads. For an M1 Mac, 2 is totally fine. Number of episodes test is going to be fine. Number of episodes full. Eventually, we're going to run 50 full episodes. But for now, we're just going to run 5 episodes for our test. And what an episode is an episode is a complete training data set. Or not set, but it's a complete point of training data. So it is taking your arm from rest, moving out to pick up the ball, and then placing it back. So in my case, what we are going to do is we're going to take the arm, it is going to come out, it's going to pick up the blue stress ball, it's going to place it into the box, and then is going to return itself to its resting state. Now, when I click play here, it's going to replace all of these individual places we're going to do, and we're now mostly set up to be able to do our first test recording. Now, if you want to at this point, you can run a weights and bias setup. Now, this is only necessary if you're going to be training locally on your computer. So we'll come back to do this one later. But so we'll go ahead and fold up step 10 and we'll come back and we'll do a record episode data test. So let's do our first test run with just 5 of those. And what these test run lets us do is it lets us know, yes, we're capable of picking up the object. Yes, we're capable of manipulating our arm. And yes, we're able to actually locate and move some of these things up. Now, before you start on your testing data, some really important things you need to have for your setup for your learning environment here. Make sure your room is nice and bright. Make sure your cameras are locked down and they're not going to move positions. If you move positions of your camera, it's not going to be great. Pick a consistent homing position for your arm. So make sure you're always returning your arm to the same location so that it's always starting from the same location. The thing about humans is that we're really good at starting from this position or starting from this position all around, but a robot expects to start from the exact same position. So do your best, and the ACT training model will kind of help us sort out some of those inconsistencies as well. Now, you probably don't want to look at the follower arm. What I suggest you do is, rather than looking at what the follower arm sees, you should look at the camera models on your computer as well. So running on rerun or so on. That actually makes it a little bit easier, because if you can't see what you're doing through the cameras, the model also can't see what you're doing. And then make sure you got some free space. These are some pretty big video files. Now, right now, we're going to be using display data as false. And then when we actually do our recording, we'll display our data as false as well. But the display data as false is going to cause that rerun to not show up. Some other things to note, and we'll get into this a bit, is some keyboard shortcuts when we're recording some episodes. So a default record time is 60 seconds per episode. And then a default reset time for the environment is also 60 seconds. So what we're going to do, and let's take a look at this. I will pin down my webcam so you guys can actually see what's going on here. So what we're going to do is we're going to grab the arm out. It's going to come over our speakers and it's going to say, start recording episode X. We will manipulate our arm. We will pick up our blue stress ball. We'll place it in. And then we will come back to rest. Then we'll press the right arrow key on our keyboard. And it will ask us to reset the environment. We'll move the things back to the exact position that it originally was from. And then it'll ask us to press the right arrow key again. And then once the environment is reset, then we can come back up. And we will repeat this over and over and over again. And now in this case, we're only going to run it 5 times. Now, before we can do that one last time, we also need to set up a correct video codec. Now, Mac, I'd suggest you use the H.264 video toolbox for hardware accelerated encoding. For Linux, you can just use Auto, and Window, you can also use Auto. It works best if you have CUDA cores for this, which is an NVIDIA-based GPU, but you don't need it. I have also done the training on AMDs, and it still does run just fine. It's just not as quick. So let's go ahead and build this command. Now, we're going to do just a 5-episode test recording. You'll notice our command looks a little bit different. It's now LeRobot-record. These 3, robot type, robot port, robot ID, is the same. Your robot cameras is the same. You might have more than one camera. I only have one camera set up for this just because my computer cannot handle doing the recording for you and having additional cameras set up at the same time. We have our leader. Our display data is false. If you'd like to, you can change display data to true here if you want to. So you can come back up into this string and you can have display data equals true instead of false. And then you'll have things run up on your rerun IO. Now our number episodes is 5. You'll notice that our dataset repo ID is our username and then the name of our file, our blue stress ball tutorial. And then because this is just a test, it records _test. When it comes time to do a full true recording of 50 episodes, this _test will not get added to you from my notebook. It'll just straight up get added. We're going to add 5 episodes. It has a description of our single task. Things work best in the ACT training model if you are training just a single task at a time. Try not to do too much. Our stream encoding is true. Our specific codecs is video toolbox. If you're using Linux, you might need to change that. And then our encoder threads is 2. So I'm going to grab all of this. It's a lot of commands and a lot of different flags inside there. And then we will paste that inside of our LeRobot tutorial. We'll press return, and we'll get ready to actually do some recording and some training here. So let's take a look at both. Now, inside of our terminal, it's going to do some thinking, get things ready to go. And
recording now, episode 0.
So now I'm welcome to come out, grab my arm, place it inside the box, and return back to home. At this point, I'm now going to press the right arrow key.
Reset the environment.
And it's going to ask us to reset the environment. So now I'm going to try to move it back to the exact position that I had it before. And I will press it again.
Recording episode 1.
So now we're going to come to episode 1. Again, I'm going to try to do the exact same movements that I did before. You want your recordings to be as close to the same as possible. I'll press the right arrow key again.
Reset the environment.
And it's going to wait for a full 60 seconds until you press that right arrow key. Now I'm going to show you what not to do. Now you've seen up to this point, my arm
recording
has come up
2.
And I've grabbed it from top down every time. Now what you don't want to do is
the environment.
This. I'm going to press right arrow key again.
Recording episode 3.
You don't want to try to have a different way of picking up the ball every time. Because if you do this, the LeRobot is not going to know how to pick things up. Now I just made a pretty big mistake there. So I'm going to press the left arrow key.
Reset the environment.
And you'll notice it's actually going to allow us to exit loop and re-record the last episode. So if I made a mistake like that, I can now re-record the last episode. So now I can press right arrow. And let's re-record that properly. Now, I find it easier to manipulate my arm with 2 hands with this gripper personally. And my computer laptop is getting in the way.
Reset the environment.
I'll reset it one more time. And then episode 4 will be the last in our 5th episode because it is, of course, a 5 index 0-based system.
Recording episode 4.
So this is the last episode. We'll go ahead and pick up this ball one last time. I will place it back and right arrow key.
Stop recording.
Now it's now going to stop our recording. It's going to disconnect. And at this point, it's going to start uploading your data to the Hugging Face hub. Now, keep in mind, you do not want to have any external users inside of your webcam data, so you probably don't want it looking at other people getting inside of your webcam space from what your other webcams are seeing, because this is public facing data. So upload some metadata with us, and now we are up and ready to go. So we should be able to actually see some of this data now. And now you've verified that your recording works, you've verified that your uploading works, and let's check now what our data set actually looks like. Now, a quick note on debugging. If you happen to crash while you were doing that recording, you can add the flag called resume equals true. Now what this will do is this will take your current recordings, it will add in some new data sets on top of that, won't delete your past recordings, and will add onto your blue stress ball tutorial _ test version here. If you do not add this resume equals true, what's going to happen is and you try to run the exact same test again, LeRobot's going to say, hey, this directory already exists, and we're not able to record into a directory that already is there. If that does happen, you can always go back to your library of .cache or your main user .cache/huggingface/robot, and then your username and your data set in this case. So you can always delete that local cached folder before it gets uploaded, and then you'll be able to do that again. Now, pretty regularly, I will use this resume true because recording 50 or 100 sessions in a row can be pretty time consuming. So I will record some of these over the course of a couple of days, and that's okay. Now, let's do a manual data replay to see what some of our data actually looks like. So we can actually replay any recorded data episodes that we want. And this is not any sort of AI training at the moment yet, but what it does do is it says that, hey, you actually have data online and you can actually see your arm moving by itself. It also lets us see what we recorded, and we can check our own calibrations as well at this point. Inside this flag, we have a flag called dataset.episode equals 0, when you can change to whatever episode number that you want to run. So let's go ahead and build this. We have a new command called LeRobot-replay. And you notice that in a replay, we don't have a leader arm anymore because we're only going to replay data for our follower. And then we're going to grab our specific repo ID, which is the one from Hugging Face itself, and the dataset equals 0. Now you can actually run this exact same command from my repo as well, because these are public-facing data sets. You could grab the bprat/blue-stressball-tutorials_test, and you could run any sort of episode 0, 1, 2, 3, or 4, because we recorded 5 sessions, and you can run it on your own computer. So let's go ahead and actually run this. So if we take a look at the webcam view here, and we press return, we can see that LeRobot is going to open up our follower arm, and it's going to rerun those exact motor positions.
Episode.
And we can see that it took us a little while to be able to open that up. And if we can see that we are picking it up, and we can verify that our data works as we would expect. Now, I'm actually noticing something that was a poor example. On some of these training datas, my claw picked up like this. And on other training datas, my claw picked up like this, with the camera facing down. It's really important that your claw position stays the exact same. And we can actually verify that even further instead of just having to replay some of those data with visualizing a data set. Now down here on step 13, we can actually take a look at all those individual camera angles, all the individual gripper angles, and so on. So now that we've done a test, let's verify that some of our data is actually good. Here's what you want to look for: that your camera angles are consistent. Now, if you took my advice and you put everything down and you locked it down in place, you would expect that all your camera angles should already be consistent. You want to make sure that you can see your gripper all the time and that your object, you can see it all the time. You can have a camera behind, you can have a camera directly on front, you can have a camera at the side. Does not matter where your camera is, as long as you can still see your gripper and you can see that object grasping movement as well. You want to know that there's smooth motion, you're moving slow and articulated, you are not moving, jumping around. And then we want to see that the tasks actually work every time. We can flag bad recordings and record those or remove them. And then we want to see that there's no bad data from that specific joints. So let's go ahead and run this data here. And now we can actually open up our visualizer to our specific data set. So we can either open up the main website here to be able to actually visualize the data set, and you can type in your username and a slash and then your specific example. So for instance, if I go into LeRobot / high quality folding, I can actually look at some data that LeRobot has put together in their own training to be able to see how they have set up for their high quality folding shirt data. So you can actually run these specific ones on your setup as well. So we've got images for left wrist, we've got images for the right wrist, and then the main base as well as their language instruction, fold the t-shirt properly. So we can actually see that they are running a rather complex task to be able to do a full shirt fold on this as well. So we can see that they have recorded 1,200 episodes in total to be able to get this up and running, to be able to get such a complex task like folding a shirt. Now, to do a much simpler task, you are not going to need 1,200 episodes to be able to do this. So let's go back to the visualizer and let's grab our data set that we just recorded. We'll paste that in and then we'll select go. and we can take a look at the data that we just recorded. So here's episode 0. We only had one recording on this, and we can see our individual arm movements as well. We don't have any specific positions that are flatlining for a very long time, anything more than we would expect beyond that as well. So let's take a look at episode 1. And we'll probably see that some of our data is inconsistent here because we have different record gripper rotations, because I believe at the start I was rotating down, but at episode 4, we'll see that I probably rotate the other direction. Oh no, I do actually record on the bottom one. So you want to verify that you are doing things the exact same every single time. And again, as humans, we're not built the exact same. So there you go. Episode 3, that is a bad episode that I would probably want to be able to go back and re-record episode 3, because that is a poor data set. It's going to end up with some inconsistencies on my data. But this is just a test, so that is okay. So now it's time to actually do a full training data. Now, we're doing a simple test. I highly, highly, highly suggest that you do not do a full recording set with 100+ episodes for your very first try. Let's just try to do a very simple task like moving a block, moving a ball into a box. As you start to get more comfortable with the ACT training model, then you can start adding in some more complex tasks, but don't go overboard right at the start. It's the quickest way to pull your hair out and get frustrated with your lack of progress. So once your testing data looks good, we're now able to do that full run. Now, as a note, inside of this training data, originally, my tests add in _test to your data set. This is not going to add _test. It's just going to be your full data. So our target is going to be to record 10 different recordings with 5 different locations. And this is from LeRobot's tool here. So their notion is, what you want to do is you want to have 1, 2, 3, 4, 5 different locations for your object, and each position that you're going to pick this object from, you want to have 10 separate recordings of that movement happening inside. And the reason we want to have 10 different recordings for each individual place where you have this object is that you want to make sure that your arm has enough data to be able to verify off of. If it doesn't have enough data, then it won't be able to learn off of that as well. More is not necessarily always better, but 10's a really good start. They also have a nice checklist here from their official guide for what good data looks like. So for image quality and setup, you want to have at least 2 camera views. Again, for simple tasks, I've personally found that 1 camera view is good enough. Steady cameras, neutral lighting, consistent exposure focus. You don't want to have leader arm frame, obviously. You're only moving following objects, so you do not want to have your finish points moving all over the time. And then if you can, your resolution should be under 720p. 640 by 320 is a great resolution to record from, because these camera models actually don't need that many pixels. Too many people think that you need 1920 by 1080p to be able to do some recording. You don't actually. So on Linux, there's far more open for the camera modules that you can change the resolution down, which is better. But on Mac and Windows, it's a bit more restricted. So you are kind of stuck at a high resolution. That's particularly why I'm using a high resolution here. So that is something to keep in mind. As far as your meta protocol, if you've been following along, you have the SO101. Your camera frame rate should be as high as you can, 30-ish. And then in terms of feature naming, you want to make sure that your camera has these correct locations. So for instance, you might have wrist.left or camera.birdseye or whatever have you, because this will also help the model know where it is from behind. And then your task annotation, avoid vague names and 25 to 50. But if you've been following through with me up to this point, you should be ready to go for your full actual test. So let's show our command. And then now it's time to actually do our full record here. So we have our LeRobot-record. We have our specific points for our cameras. We have our leader arm. We're displaying data as false. Again, this just kind of helps save some resources. Here's the new dataset repo. You'll notice it does not include _test. Your number of episodes is 50. And then you have your specific data tests and so on and so forth. So at this point, you can actually do this full record, and just to show you, the recording is the exact same. So if I were to run my data in here, the recording method is the exact same as it was for your test recording. So it's going to spin up just like it did before. And recording episode 0. So I'm going to come on up, make sure that I'm doing consistent positioning every single time. Come on in, place it inside of my box, return back to home, and then press the right arrow key.
Reset the environment.
Reset your environment, put it back to where you picked it up the first time, and then press the right arrow key. I'm actually going to Control-C to break out of this recording because I don't want to actually do a full recording and upload all of this data. But at this point, you can actually go ahead and do your full recording for all 10 of those tests, or for all 5 of those positions. This will probably take you anywhere from about a minute for each specific recording. So if you're going to be doing 50 episodes, it'll take you about half hour to 45 minutes to be able to do this all, depending on how quickly you can actually run through your data as well. So best of luck with that. Now, during a recording, what happens if you accidentally crash? Yeah. So sometimes that will happen. If you're using a slower computer, if you have to come back to it, or if you're just recording a lot of episodes and you want to record these on different days, that is okay. What we're going to add in is we're going to add in the flag resume equals true. And then you also have to change the number of data sets to remaining episodes only. So for example, I have this full command like so, and I have a number of episodes is currently at 50. So what I'm going to do is I will paste my data set in. And let's say, for example, that I crashed at, say, 30 recordings in. So I still have an additional 20 recordings left to do. My number of episodes is actually now going to be 20 because I want to record an additional 20 episodes. I do not want to have the total number of episodes that I'm going to do at once, because otherwise I will record an additional 50 on top of that, not something that I want to do. I'll put in another / here, and I will say resume equals true as that as well. And with that resume equals true, it will be able to allow you to resume into that. So I can copy that, paste it into my terminal, and I'll be able to resume off of from where I left. So at this point, you've recorded your data sets, they're uploaded to the Hugging Face hub, and you've now visualized your data, checked that everything looks good, and now it's time to actually train your policies. So this means we're going to take that data and feed it into that transformer so that it can be able to start chunking some actions for us. And at this point, you have 2 sort of paths that you can take. The first path is doing local training on your own machine. I'd recommend this if you've got a more powerful computer, as well as having a NVIDIA graphics card. If you have an AMD graphics card, you can't really take benefits from this, and you'll then be going on to CPU-based training. The other option you can do is doing your Colab training. So you can use Google Colab's GPUs. They're a little bit stronger, and you should be able to get things done a little bit quicker. So if you've got a strong GPU, you can move into local training. If you don't have a strong GPU that is NVIDIA, I would go into Colab training personally. So at this point, skip forward in the video if you are going to be using Colab training. Otherwise, let's talk about how you can get the local training going. So on the local training, everything's going to be run directly on your machine. So you're going to be running the LeRobot_train.python file to be able to use your training from the data that you'll be able to put in. Now, throughout your training, checkpoints are going to be saved. So every 20,000 steps, we'll talk about what that means in a bit, you're going to get some saving for that as well. And then if you want to, you can also have something called weights and biases, which is kind of like an online check to be able to check how your training is going and how long it is taking. And then when your training is done, it should automatically upload that training to the Hugging Face hub as well. So to be able to do training locally, you have to make sure that you've already logged into your Hugging Face. Now, at this point, you can do your Hugging Face auth, who am I, just to double check that it knows who you are. So Hugging Face auth, who am I, and it knows that I am B Pratt as my username. So I am ready to continue on. Now for our Hugging Face details here, we're going to fill in the details that we put in for our training set. So in my case, this is the same as what we did up above. So this was blue stress ball was the name of my training data. And then describing my task is place the blue stress ball in the box. And we'll run that. And then we'll do our weights and biases login. Now, we haven't talked about how to do this yet. So we would type in W and B login. At this point, it's going to ask you to be able to put in your key just like you did before. So if you go to weights and biases.ai, sign in and make an account here as well. Once you have an account, you can then go into your API keys. And then when it asks you to type in your API keys, you can put it in like so. I've already signed in with Google, so I'm going to pull in those API keys. If I scroll down here, we should be able to get to our keys themselves. Make yourself a new key and then copy and paste that in. Now again, I'm going to hide my screen so that you can't see any of my keys personally. Similarly, make sure you copy this down because you won't be able to get your key again. Now, once you've logged in, it's time to actually run that training as well. So I'm going to build out my training command here, and it's now going to be changing directly into LeRobot and then grabbing a specific Python file. It's going to be our policy type is act. That's our action chunking with transformers. Our dataset repo ID, of course, is the one we did up above. And then for your outputs, I'm going to say policy as my end because there's now a new policy trained. Our job name is our training model, and then the name of our data set. Our policy device is CUDA. In my case, I'm not going to be using CUDA. If you have a CUDA driver, you can use that. Weights and biases enable true. You're welcome to set that as true or false, depending on if you want to use weights and biases to check that. And then your policy repo ID is what your finished policy is going to actually end up coming back at. So because I'm not going to be using CUDA, I'm going to copy this over. And then because I'm on a Mac and I don't have CUDA, I'm actually going to change this policy device to MPS as opposed to CUDA so that I can use my Apple Silicon. Press return and it's going to start doing a training for us now. Now at this point, you should start seeing some training pop up and your steps actually starting to calculate how long it takes to do each of your steps. Now, I'm not even going to bother doing a local training on this because I'm doing a lot of extra recording. I have a lot of extra things added on the background, and my steps are going to be so infinitely long that it will take me 30 years to properly train a policy. So if you're training locally, jump forward in the video to when we start talking about training data and what those outputs actually mean to explain how this actually goes about. Now, if you're like me and you're running on some older hardware, you're likely going to have to run a Google Colab training. I would also suggest that you buy some compute units for this as well, because the free compute units do take a long time. Now, in this 5B section here in the notebook, I do have some ability set up so that you can resume your training because there's a few caveats that are helpful to know with the Google Colab training. So the first thing we're going to do and to know is that the Colab instance is going to install its own version of Conda and LeRobot inside this instance itself. Your data set's going to get downloaded from Hugging Face, so you don't have to transfer anything around, which is nice. Your training is going to run in the Colab session, and then your checkpoints are going to get backed up to Google Drive, so you're not going to lose your progress, hopefully. And then your finished policy should get automatically uploaded to the Hugging Face app. So to be able to give you an idea of how long some of these things are going to take, if you use the H100 or the A100 GPUs, it should take anywhere from an hour and a half to 2 hours. You're using the T4, it could take 5 to 6, even longer, depending on where you're at as well. And I highly suggest you don't do CPU only. So what that means, if you come up to runtime, you select change runtime type. You can choose CPU, H100 GPU, G4 GPU, A100 GPU, L4, T4, whatever. I would suggest you use the A100 GPU. This is the fastest one that I have found at the time of recording. It's going to ask you to change runtime attributes. It's going to terminate your current session. That is okay. So you can select okay for this for now, and then click save, and it's going to reboot your connection. That's fine. Now, if you don't have Colab Pro, what's going to happen is that you are not going to have running in the background capabilities. So you can't just let this run in the back. You have to keep your browser tab open, and you need to make sure that you're not going to get rid of your instance that you're actually running inside this. So some things you're going to need. You're going to need a Google account that has, you need a Google account that's got Google Drive. You need your Hugging Face account with a write access token. And then you also need a weights and biases account. You don't need it, but it is recommended. Now, inside this secret panel, we're going to put a few things in here. We're going to put in our Hugging Face token and our weights and biases token. Now, I already have both of my tokens added in, so I'm going to provide notebook access to both of these. So you should go ahead and copy paste in your Hugging Face token and your weights and biases token. If you don't know weights biases is, if you go to weightsandbiases.ai and then go to settings, you can generate an API key just like we did with the Hugging Face. And you can also scroll back up earlier to where we had our previous section with our Hugging Face API key, and you can use the same key for this. That is totally fine. So now what we're going to do is we're going to actually start running with the install on here. So I can click play. It's going to install Conda Colab onto our current instance of Colab. Now, once we're done installing this, what's going to happen is it is going to crash, and that's okay because it has to restart our kernel. You don't have to restart your page or anything like that. Don't worry about that. Next, we're going to make sure we have the latest Python version inside of Colab. At least at the time of recording, Colab has Python 3.1 as default, and we have at least a 3.12. to be able to get into the LeRobot repositories and things like that. So we're going to install the latest Python version to make sure we're still up to date. And again, anytime you start a Colab training up again, if you happen to crash, you have to run all of these cells again, and that is okay. Okay, so we're now on Python 3.12.13, so we're now up to date. We're also going to go ahead and install LeRobot, so we'll go ahead and run this as well, and it's going to clone the repo, just like we did cloned on our local machine. We'll also do a clone over to the Colab instance as well. Okay, so that took a hot minute, but we're finally all installed now. Now you can do your weights and biases login. Provided you've put your token into your key here, it should automatically sign you in and you should be ready to go. So now we're logged in as our specific user. We also have to log in to Hugging Face. We'll do the same thing. You should be able to also just click run and you should be ready to go. And we're logged in as B. Pratt, which is of course my Hugging Face user in this case. Now it's time to configure up your training job. Now, in my case, you need to put in your username. Mine is B. Pratt. And then your dataset ID. Mine is blue-stress ball. So this is where you need to type in what you had before. And this will start configuring that up. And you can go ahead and click run. And it's going to ask to connect to your Google Drive. Now, you do want to connect this to Google Drive, yes, because what this is going to do is this is going to create some persistent storage for your checkpoints. So on Google Colab, what can happen is it takes some time for the training to happen, several hours. So it's possible that you actually lose some of your progress because your session times out. So rather than having to restart your training all over again, what you can do is you can connect it to Google Drive for persistent storage. That doesn't mean that it will install the LeRobot again, because you need to do that every time. But it does mean that it will save you literally hours of training time if you're on a free version or even on a paid version as well, so that it keeps things. And what will happen is this is going to output to a Google Drive folder as well. So now it comes time to actually run the training, and we can actually run training with an automatic resume as well. So if you click run this, what is going to happen is it's going to run the same training policy before. It's going to change our directory. It's going to grab our repo ID. It's going to make our policy act or action chunk of transformers. Our output directory is Google Drive. It has our job name. We're going to use our CUDA cores, weights and labels true, and then our policy ID is our repo ID with the policy ID added to it. So if we do have a valid checkpoint, it's just going to resume from that latest checkpoint that it grabbed. Otherwise, it's just going to start fresh training. So even if you're going to resume this, you can just go ahead and click play on here. Now, I believe that I already have solid training data, so I'm going to go ahead and remove that. So now I've removed that from my Google Drive folder. I'm not actually going to resume from a checkpoint. So I click play here. It should actually start running my main training. Now, because I've already done that training, I'm going to show you now what a training actually looks like. Now, when it comes to what your training output's actually going to look like, let's take a look at what a training output is. Now, this is a training I did on a previous date. This is in a Colab training, but it does not matter whether you did local or Colab training, it's going to look the same. So as I ran my Colab training here, it's going to start pulling out into what a training is. Now, this was a training that resumed from a previous checkpoint. So I'm going to say, it found a checkpoint and it's going to start resuming from that previous training because I ran 20,000 steps, my Colab instance crashed or my local training crashed, and then it saved a checkpoint at 20,000 steps, and then I'm able to resume on. This information here at the start is just showing what our current basically parameters are for your training model. And for the most part, you can just kind of scroll over through this. The part that we really want to get to in the meat and potatoes section of it is right here when we actually start doing our main training. And this is what it's going to look like at this bottom section here. So let's break this down a little bit more. When we look over here on this training, 0% is of course the percentage of the training that is completed. We are 0 out of 80,000 steps presently because I've already done 20,000 steps on the previous checkpoint. We then have 16.29 steps per second on the current training. We have the amount of time that's currently elapsed and the amount of time that's going to take for the training to finish. These will constantly update. So on a A100 GPU, I was doing about 16.3 steps a second. When we look at the number of steps I've done, is 20,000 steps. Now, when we think about a step, let's go back to when we recorded our demos. So we had a single recording an episode. We had the entire episode where you started from the resting position, went to pick up the ball, moved in the box, and moved back. That's a full episode. What the ACT model does is that slices that up into a bunch of different individual steps, and it chunks it out and says, you might have, say, the next 100 frames. So you might have, in a 10-second recording, you might have something like 8,000 steps or something along those lines. Basically, how many individual chunks do we have? So of those chunks or those training samples, what our transformer is doing is it looks at one chunk and it says, okay, if I stand here, I'm going to try to predict where am I going to go to next. So I might say, given what these images look like and my current joint angles, I'm going to see where I'm going to be 100 points from now. And then it checks how wrong it was using that loss parameter. And then it sort of nudges those weights slightly. That's what our loss rate is. We want to try to get our loss rate lower, but not so low that we end up what's called overfitting our model. So a loss that is too high means we can't predict accurately. A loss that is too low means that we are overfitting our model and we have to have two specific exact scenarios for that to be able to happen. When we think about an EP, that is an episode, we've run through 607 full episodes up at this point with 20,000 steps. And then an epoch is the number of times we've gone through the entire training data set. So because this training data set was only trained on 50 models, by the time we got through 20,000 steps, we've gone through 15 epochs in total. Now, if we keep scrolling down through this training data, we can see as we continue to progress through that training, we can go all the way down. And at a certain point, you're going to hit a checkpoint. And you notice right here that we had a checkpoint policy after 40,000. This gets uploaded to either the outputs training folder on your local drive or to your Google Drive outputs folder if you're doing the Colab method. And you're going to have those checkpoints saved at 20,000, 40,000, 60,000, 80,000, and 100,000 steps once it's all said and done. So by the time we're all done our training, at 100,000 steps, we've done 800,000 samples. We've done 3,000 individual views of our different episodes, and we have done 75 total epochs with a loss of 0.039. So I could probably get that loss even a little bit lower if I had some better data going into this. Once your training's all done, it's going to then actually upload your data automatically to the Hugging Face cloud, and then we can take a look at that data set just like we did with that visual data set earlier. So if I now go to, it says the model is now pushed to this URL. So if I go to this URL, we can actually take a look at that policy. So let's click on it and we can go to a new tab where we can now actually see the model that was trained. And in here, if we go to files and versions, we should see that we have our full data here as well as back to our model card. And that is a fully trained policy. So now at this time, it's actually time to evaluate your model, or what's called inference. And at this point, we actually, with our policy training done, we can actually run it and have it do it autonomously. And it should be able to pick up from some of our errors. And I'll also show you where some of my recordings went well and where some of my recordings did not go well, because my policy is not perfect because I did not do enough training data as well. So this is very similar to some of the commands we've done before. But some things to note here is that we do not want to touch the arm or get in the arm's way. Similar to like we did with the actual recording data, it should be in the same environment as it did with that as well. We should also try to have that brain moving back to where it is. So this is also going to save those evaluation policies to the Hugging Face hub as well. So make sure you check those camera positions as it goes. Let's run at least another 5 to 10. So I'm going to go ahead and run this command to be able to grab our main command here. And we're doing LeRobot record. And then we've seen all of this stuff up to this point. Our repo ID is going to be eval_blue stress because it's going to be evaluating it. And then we're grabbing a specific policy path, which is one that I've already trained. Again, you can use my specific policy here and see all of its flaws as well. So let's go into our terminal now. So we'll run that last command to be able to do its evaluation. And let's take a look at how resilient this arm is at being able to pick itself up. So we'll wait for it to start running its command here. And here we go with episode number 0. So it's going to move out. It's going to try to find that blue stress ball. It's found it. It's going to attempt to pick it up and place it into that box. And we've got a pretty successful first train, and it's even resilient enough that we can pick it up, mess with it, and say, hey, robot arm, you forgot to pick up the ball. So now it's going to come back and say, hey, that ball isn't supposed to be there. Let's try to pick it back up and put it back into the box again as well. And overall, pretty resilient in this system here. So that's a pretty well-trained policy in that specific position. So let's talk about why some of your training data may or may not work. One of the biggest things with mine is that when I was running this section here in specific places, sometimes I place the ball like this, sometimes I place the ball like this. Sometimes I had the claw picking it up in this direction. Sometimes I had it picking up in this direction. And because of that bad data set, you end up having a pretty bad environment that's able to pick it up, and it has a hard time recovering from. As well, I only recorded 50 episodes, and 50 episodes is not a lot for me to go down to. So if I wanted to get a much more robust training model, I'd want to get more into the 100 or even 200 versions of recordings. But for the most part, to be able to get something that's even able to reproduce that little small sequence is pretty darn impressive. Now, let's see what happens when we move it out to a different position and see just how resilient it is. So before we were directly in the middle here, let's move it over just a little bit and see how resilient we end up being able to make this system as well. So we'll see what it looks like when it is just slightly to the right by about 2 centimeters. We'll see if that's enough for it to be able to pick it up. Likely it's not going to be, because I've just done 50 training models and not enough in this sort of range, because I have one here, one here, one here, one here, and one down here, but none directly in the middle there. So it might not end up having that working as we would expect. So let's see if it's able to pick it up in a different position. So overall, not really able to pick it up in that position. But if we move it back to the original position, it was able to pick itself up from originally. we can see if it's going to be able to recover itself back up again. And looks like it's not able to recover from that position. So as we move things around, it does have a harder time recovering from some positions rather than from others. What would we do at this point? Well, at this point, one of the best ways we can do this is just by adding in more data so that it's able to have more training data to be able to figure out where it is at. But again, when we move things back to its original position, it is okay at being able to pick itself up and grab that ball from the original position that we originally trained from. And we'll see, we may have confused it there by doing a bit too much. There we go. So we can see that from that original point, it's able to complete its task pretty successfully. So to finish this all off, I've got a bit of a troubleshooting reference for you down here that you can take a pause at and take a look at, or take a look through my notebook. Best way to make your model a little bit better is just by doing more consistent training, and you will get better at training your own models as time goes by. I hope you found that a useful tutorial in being able to train some of your own robotic AI arms to be able to use the ACT model. Let me know if you got any questions, you're running into problems, in the comments down below. I'll do my best to answer them for you. And as always, best of luck with your next robotics project.